too hot.
No, no.
So
That
that's
is one
great.
thing that doesn't. Although it can be fairly warm here, and it's like it can be humid down south, but up here it seems to be kind of a maritime climate, so it's quite fresh. Even when it's hot, it's still kind of a breeze or something. Okay,
that,
so
does it rain a lot? Or
yeah, I mean, there's a good bit of rain.
good about rain?
So somebody I know pointed out that Ireland's this little island on the edge of a very big ocean, and so
Oh, is that Atlantic Ocean, right? Atlantic, right?
yes, exactly.
Not too far from where you are.
Yeah, exactly. It's just down the road.
Shore. You have the shore there, huh?
Yeah, I'm right beside the sea. So, but I mean, I wonder, would you technically call it the Atlantic, or is it the English Channel or the Irish Sea?
Oh,
So, English Channel is between
oh,
London
that's
and France or whatever. So, but yeah, no, I think it's probably close enough to the Atlantic, but maybe the Irish Sea.
it's a part of tributary type.
Well, the Irish Sea is between Ireland and Great Britain.
Okay.
Oh, it's the wrong one. So what are we looking for today?
Yeah, should I go over a little bit of? I have done a little bit. I don't know whether that will help, but I can present that a little bit to review if you want to.
Yeah, exactly. I think if we're going to do some coding,
yeah,
we would need
we'll
to
go over
like
it.
work out a plan of maybe like just four-line plan of what it is that we're going to do.
Okay, so I'll share this one. Let me start. I have to move it.
Now, hover over that.
Are you able to see now? You see?
Yeah,
Oh, okay.
you're sharing it. Great. Oh, so you have the ability to just share. I don't have to.
Does it automatically?
Yeah, so that must be because you are admin. So does that mean you can mute people as well? I don't know.
So I have limited thing. I cannot let people in or anything like that. But
oh, okay. Okay, so you can share whenever you want. That's good, because I was about to share your screen, and all it said was remove, and so I was hesitant to click on that, or else, Then I see you're sharing it anyway. So
yeah,
I'll get a pen and paper here and see what notes we need to take. Should be. These are all the notes I have.
Yeah, you are a good note taker.
Yes. Well, I had to when I was looking into your work there. So I had to write it out, because there's a.
Yeah, it's a good idea. I used to do that, but I somehow got. I mean, sometimes I write a lot.
Yeah.
So you have to write like Cornell notes. They call it different types of notes. And they're teaching kids how to do that. But I tried a lot of different things. So, but I like to, try to remember. So I don't, if I can not write too many. That's why this one is helpful.
You can kind of go back
there.
Yeah, that's good.
Yeah. And also when the audio is recorded, so that's a good thing. And that's what all things that IT could do. I mean, we'll talk about it later. I have things here, a little bit about IT, but I probably will not go through that.
So are you? All I can see is sort of a sketch with luminous phase and inertial subluminal matter. Is that what you're sharing, or?
Oh, I don't know why.
Maybe it's frozen or something.
Let me see.
Or maybe you're looking at a different thing that I can't see. Oh, now
So
it's
now
moving.
it's doing it. Oh, I cannot reduce the screen. If I reduce the screen, something happens. I thought that I can reduce the screen, but it's okay. I'll just put it like that because I want to see what you are seeing. So I thought that I reduced the screen size, but that doesn't. Then when I move it, it doesn't do that. So now, let me see.
How are you reducing the screen size? I don't get. How is that happening?
Oh, there is a reduction, right? That you put the square one on top of the of the screen. There's a square on top which increase that can reduce the size of the screen.
Oh, okay.
Minus and then yeah.
Is that Oh yeah, you mean this? You've X the square and then the line.
Yeah, about the where you have all the icons on top. Next to that, at the end on the right, there is a square one. You press that, you can actually reduce the screen.
Yeah, I'm just wondering, is that on what, Microsoft, or is it on StreamYard that you're doing that?
There in all the even all screens it is there.
Oh, okay.
So
yeah.
Now I think it's moving. Okay.
Yeah.
See, I want to see that it's moving. Okay. So I can kind of see it.
I think nearly the other ratio would have been better.
We did over
Rajan. Well,
yeah.
When it was bigger,
So
it was probably it fit on the screen more.
Okay.
If you want to go back to the, I don't know, it's up to you.
Is it better now? You say?
No, it's still the same sort of dimensions.
Oh, okay. Okay. So I had to adjust.
Yeah, it was
Is
good.
It better now?
Oh, yeah. That's it. That's perfect.
Okay. So we were talking about a couple of weeks ago. This one, we know that. So that is the superluminous thing, and I believe your anomaly when I watched your presentation, which is all now funded for you from the European Space Agency. You are doing a PhD. I think it may have direct connect. Eventually, I think indirectly that's a solution to the problem in a way. It answers some of the questions, because the whole question I am now rethinking, and I think that is I'm doing the physics reshaping. It all falls down, falls through from the formalism as well. It's a derivation, and that's a good thing, because I believe in derivative process, that one needs to another, things like that, so that you have a sequence of steps or algorithm.
Yeah.
So that's all seeming to be working out fine. So what I'm showing is that this is a superluminous thing that we believe with Emmanuel, everybody, that and then John, everybody, that superluminous plenum may be the thing, and it is magnetic. It has monopoles and everything. So it's highly turbulent structure. So in that turbulent structure, like the ocean, like Atlantic Ocean, you can have places. If it is infinite, you can say, actually, I mean, eventually I like to word it like that, and probably a mathematician might define it more accurately, but I would say there exists within a turbulent superluminous magnetic plenum the monopoles. They arrange the vortex field and the gradient field vectors can arrange themselves. They can orient themselves such that it can produce locally some anomaly. The anomaly is is the formation of the Helmholtz decomposed field that we are talking about, original Immanuel on myself paper of theory of Doom. So that's where it starts from. So we can say in an inferent thing, probabilistically, there is always place where the vectors can orient themselves in a preferential way. Okay, so that probability exists because the infinite thing, there may be some places where they can occur. Okay, there is always that probability. We can actually prove it mathematically also, I think, eventually, from mathematical theory. But let's for now take it, from physical mathematics, just that aspect, which I think can be proved. So
Okay.
when you go down, that is an anomalous medium. The superluminous planum is turbulent, but it's an anomalous medium. Again, we have to kind of prove it. The group velocity, and it is written in the, if you go to Wikipedia and all of the literature, it says that group velocity can be greater than the fastest of the individual or phase velocities. So,
Yeah.
and this is actually partially proved by some of the people we are talking about. I think Luca, Lilly, and all that Emmanuel is talking about. Hopefully,
Yeah.
when
So
they, yeah,
group, sorry, when
yeah,
you say group velocities, is that of the wave function?
yeah, the group velocity. Okay, so I think that from here, when I put it here, at the Planck level, you have this situation, right? I showed, yeah, this where, yeah, this shows in a way the whole thing, that the Planck, I think the Planck sheets are like photon like, and then you have the vortex things, loops, which are the vibrational things. So we can actually derive that. That's the gradient is the light thing, the vortex thing is the vibrational thing, and that goes all the way to Planck level. Now, when they arrange themselves, like I'm showing
what is
here,
vibrating? What is vibrating in that? The plenum, is it?
yeah, the vortex field make it vibrating.
Oh yeah, vortex
Yeah,
field.
yeah. So you have the gradient, it splits up, the field splits up into gradient and vortex fields.
The vortex is the magnetic part, isn't it?
Yeah, the vibrations.
Gradient. Well,
Yeah,
but the
the
gradient is
magnetic.
the electric part, and the charge, like
Well,
in the.
eventually it becomes I think initially both the gradient and vortex may be magnetic. That's something we have to figure out.
Oh,
I would think the gradient will be more like electric like, you know,
yes.
because in a photon, actually the electric thing is the main thing. Because connected with electrons, electric thing is the gradient aspect. And the vortex thing in general is the magnetic, because
Yeah.
we believe, I mean, that's so far what we know is that magnetic field is more local, whereas electric field is more global,
Oh, I didn't know that.
Yeah, kind of. It's, I don't know whether it's completely true.
Yeah, I know what you mean.
Yeah, because electric and magnetic field exchange with each other. Maxwell equation says that if the magnetic field is moving around, like in vortex, then it will create an electric field. But electric field, when it moves also, that also can create magnetic field. So they are very highly interactive. So which one is which? Many people believe so far the electric charge is a primary thing. But what we think is that that's not necessarily the case. The magnetic thing is the primary thing. So which one came first? They got chicken, that type of thing,
Yeah. Or
So
are they
is it
unified? Are they just
Yeah.
unified in some sense, and then indifferentiable on some level?
Yes,
exactly.
exactly.
They're splitting up because of because of the energy of the universe
Yeah, the
levels.
probability. Yeah, there is always the vectors
Maybe
arrange themselves.
they're obviously unified.
Yeah.
So at some levels, so maybe at a higher energy, they're just one one thing, or well, they are one
turbulent.
thing.
Yeah, when it's turbulent, monopoles, they are not oriented. They are random. They are
But
fluctuating in random.
I would say that the monopole. I mean, when you go to monopoles, it seems like you're going maybe even further than you're dividing up the, or you could say you're unifying, I suppose. But you know, you're definitely leaving out the electric part at that point. You're
Yes.
totally focusing on the magnetic.
Yeah.
So
yeah,
it's an interesting question. I don't know the answer.
That's an interesting question. Yeah, it's like the egg or chicken problem, you know. But
yeah, okay.
Yeah, I don't know whether it matters that much because of the way I have developed. It may not matter that much. It is a matter of semantic or philosophical aspect than, you know, the actual problem solving aspect. So going from there, going from the, from this aspect, we came to, so let me skip this. We went over a little bit. We went that, okay, the tensor aspect, you know, when the space is a third order Spencer and then the time is the fourth order tensor, things like that comes later. So we were this one. So the turbulent thing, essentially what we are saying is that locally there could be places where the vectors can arrange themselves and produce the gradient and vortex fields, essentially.
So the purpose of the tensor is to go from one basis to another, is it? Is that
which
correct?
one? Yeah.
So
locally,
there's some
locally it's an anomaly. Huh?
You have some basis vector or something, and then the tensor transforms that to a different basis. Is that correct? Or?
Yeah, the decomposition. Yeah, it's a combined field, which I called it's a combined field.
So the tensor is describing
it's a combined field of,
and is it describing randomly the way bending the space, or is it describing the way the field is bent in space, or?
Yeah, the field is all over. It's random, so it may be at some point it may be the vector may be pointing this way, the other point other way. So it's randomly going. It doesn't have any particular orientation. It's all over the place. You know, the vector
all over the place. It's a bit like quantum foam, or you know, that's kind of
like a foam, a superfluid type of.
Don't you have an issue there if you're using tensors? Don't they? You have to differentiate. How do you differentiate over a discontinuous surface?
Yeah. So there you cannot do anything, you know. But locally, what we are saying that you have to first describe the physics, and the physics is that locally, because of the random or locally any fluctuating thing, any random thing, locally there could exist a place where somehow nicely the vectors arrange themselves. That's the main. So they are fluctuating very well, and one of the reasons is the monopole themselves. So now north monopole may be here all clustered together, and that south monopole somewhere else, right? At some point they come together, right? And they form the dipole. So now once they form a dipole, like a horde that John is talking about, once they form the dipole, now it is defined. The direction is defined, right? So there is a definition there. The field becomes defined.
Well, they should. I think according to Emmanuel's work, it's like when the two monopoles come together, they form the electron model, don't they?
The Horn torus, eventually, yes.
Yeah.
Sensing. It forms like a Horn torus. So that's the electron.
It's the electron, right?
The Horn torus, but that Horn torus is actually magnetic in a sense. You know.
Oh yeah. I think that torus field he's describing is meant to be somehow would you describe it as the magnetic moment or the magnetic field, I guess, of the electron? Seems correct.
Yeah.
So yeah, it's interesting.
What stabilizes is that. Yeah. What stabilizes is the like Thomas precision, things like that. Will stabilize that. You know. Will stabilize the field. So the Thomas precision maybe have here.
I'm not sure what you
and that stabilizes thing.
What do the arrows mean?
The local one.
Yeah.
The
And so the
local
local
ones where they
people,
arrange themselves.
you want to differentiate over that? You saying you can do that? This is a
Yeah,
area
you
or
can
something?
do the vectors. Yeah, the vectors will arrange themselves as vortex fields and gradient fields locally.
Okay.
So they orient themselves, such a way, because the monopoles are coming together. At some point, the north and south can come together, right? They're turbulent. They're all over the place, but at some point they can come together and they can arrange themselves, orient themselves such that they form dipoles. And these dipoles are now rotating, right? Because they have energy, they start rotating and they create that electric field eventually. And you know, and now the electric vector is pointing and the magnetic vector, and it is now processing.
Yeah.
Like our from classical mechanics itself, it's proven that you get processing, when they orient themselves, when these vectors and they rotate around that. So it's like a top, when you're top, right? It has a top has an axis this way, and then the top will spin, right? Spinning, and that produces something called the precision, right?
Yeah.
So you can actually calculate from classical mechanics. It's a fundamental thing of classical electromagnetism that classical mechanics actually. It's more of a classical mechanics which is
Yeah.
applied to electromagnetics itself. Classical mechanics itself.
I should probably. I think one day we were having a conversation, and you mentioned the superposition of particle spin or something, and I was like, I was thinking that was impossible. But I was listening to some woman who's working with quantum biology. Forgotten her name. I can look it up later. But and she was talking all about these different experiments done into the superposition of spin. But so it was interesting. And like, let's say you have something that's totally spin up, and then a particle is totally spin down. But we know that with the you could have a particle that's partially spin up, but when you measure it, it will just be totally spin up. So if you had a particle that's like, so let's say it's a sphere, and the vector is pointing, it's not pointing straight up anymore, it's like off to the side a bit, but you keep going and eventually it just goes to the equator of the particle, then that's neither up nor down. Yeah, it's just in between. But when you measure that, it's going to be up or down. So I suppose when the vector is pointing at the equator, you could say that it's a superposition of spin, that it's both spin up and spin down. But I mean, is it? I mean, or is it just? Do you know what I mean? Like, it's not really spin up and spin down. It's kind of halfway between.
Oh,
so
yeah.
You could call that a superposition if you want, but I don't. And
Yeah,
it's probably in a mathematical way.
Those questions, I think, is because your external magnetic field, things like that can arrange that, because Earth is, although Earth is by itself, it has effect from other like sun and everything, right? Which can the magnetic field can affect the Earth's magnetic field, and we know even Moon and Earth has that. We call it gravitational effect, but at the gravity at the fundamental level is electromagnetics, right? That's what we are coming to. So they are all interlinked.
I think that's like a theory, pretty good one, I think. Well, like for instance, although I mean it's hard to say. I was of that opinion for a long time. So I think anyway, either way, they're all supposed to be unified in some sense. So they have to be one force.
Yeah.
And that could easily be the electromagnetic force, of course, or something else, maybe a different type of force. But yeah, it's interesting. Go on anyway. I don't want to.
Yeah. So we will pick up on that, and also we can actually look at the classical thing. I think Wikipedia is a fundamental thing about how the precision occurs. How the it's just a mechanical thing. It's a classical mechanics. Which proves, and you can say what angle it will go at an angle. The precision angle is at, it's not vertical. So initially it starts vertical, but it goes because of the gravity. I mean, the real thing is because of the gravity.
Okay.
It originates. Okay,
And
so I think there are a lot.
what does it
Yeah,
tell you then, or what do you get from all of that?
yeah.
What's the
So we'll move on. You can come back to this question because I think they are quite fundamental. They are important. But what I am saying here is that we want to move to our coding thing. So I just want to briefly forward, but I think this is very important to settle these as. So that's what I want to consider. So anomalous medium, uh, that can, essentially it proves, and a few people now come forward proving that even Einstein theory shows that there are regions where it's superluminous. Einstein didn't rule out that actually, but people eventually interpreted that way. So the velocity, if it is higher than speed of light, becomes imaginary.
You hear that a lot from people saying that Einstein didn't believe in a constant speed of light, and he kept referring to the variable speed of light. But I think that's all hand waving, like, because in a sense we have length contraction and space dilation. So from anyone's perspective, light just appears constant. So it doesn't matter if the space is contracting and expanding and the light is constant, or the light is contracting and expanding and the space is constant. Either one is they're about the same thing. Especially in terms of relativity. So I think is that what you're talking about? Because a lot of people keep mentioning that.
It's a matter of how you adjust the equation, because velocity is nothing other than the space over time, right? The movement of space over time.
Yeah.
So is it the time changing or the velocity changing?
Yeah. Well, this velocity has a vector involved, but speed, I get distance over time. Yeah.
Yeah. So velocity times time is space, right? So if the space is changing, you can say the time is changing, or the speed is changing.
It would be the distance anyway. The distance measured in some units, which you could also interpret as space then, I suppose. Yeah.
Yeah. So like the speed times multiplied by time is distance, right?
Right. That makes sense.
Yeah. So either you can, when the distance changes, you can say the time is changing, or the speed is changing, right?
Right. Yeah. So this is
So Einstein said the speed is constant. During in the theory of relativity, the relativistic level, the speed is constant, speed of light, but the time is now changing. When the distance is changing, the time is changing. So dilation of time occurs. So it's a matter of how you look at the equation, the fundamental equation of the definition of speed, time, and distance. How you use them is the whole thing.
Well, I mean, it was more. I mean, that's this sort of classical. Would you call it? I don't know what. I think they refer to it as classical relativity. Of Poincaré, and I think it was like 10 people who came up with that whole thing, that if the speed, in order for the speed of light to be constant, time has to contract or dilate, and space has to contract. So there's a lot of that work was done by Poincaré, and then the Lorentz contraction. Oh, and also Fitzgerald. Don't forget Fitzgerald contraction. He also came.
Oh yeah.
So, but then I think Einstein was about 13 when they formulated all of that.
Yeah.
Or even younger. So, yeah, I don't know. Like, we can say that he came up. I think the interesting thing about Einstein is he said.
Oh yeah.
He like, how do you say? He didn't posit it. He stated it, like he made a definite statement that this was the way it was, whereas everyone else was holding off because it sounds so ridiculous. We don't see time slow down or space contract anyway. So to be so definite about it was the issue, and maybe why he ultimately was given all the credit for all that work that was done, like before he was even.
Oh yeah.
a student of physics. But then I guess with the, obviously general relativity and the insights he had there, I think that's really what he should be more considered for, considering that most of relativity was done before he was out of school. So, but yeah, I mean, there's that. I mean, there was also the fact that maybe he didn't do the equations himself. On the Hilbert is supposed to be had a lot to do with the field. But I think the basic principle, like of the equivalence principle and all of these things and the bending of space-time, all of that comes from Einstein's head. So yeah, so that's what we should be crediting with him for. It's a very interesting idea. So so are we getting off track there a bit though, Rajan, or are we still on track?
No, that's fine. So what I just make a comment and then move on is that two things. One of them is that the equivalence or the relativistic equation, actually somebody had come before Einstein. Second one is, I think the speed of light was considered constant to have the conservation of energy. I think so. I think if not for the speed of light constant, you cannot have the conservation of energy. You cannot use the conservation of energy. I think the equations. Something like that.
Well, yeah, that could well be true, and that's like probably part of the history of physics. It'd be interesting to learn about that. I suppose the only thing I know is that it an experimental result by Michelson and Morley. Right. Yeah. So that was the kind of first indication they had, and then they often say, that disproved the ether or whatever, but I'm not sure it did. I think it just may have. There's different interpretations of it, but so ultimately they came that light is a constant from that. So then they had to explain it somehow, and that was what Poincaré was. His work was in relativity. Same with Fitzgerald and Lorentz, and there's a good few of them. Like there was something like 10. I think there was some woman involved as well. Did a lot of work in it.
Symmetry.
Names are all forgotten.
Symmetry.
Like no, it's just Einstein. He did it all, even though he was only 13 when it happened. It's bizarre, but like you said, he did. He asserted that it was true, but I don't know. Like anyone could assert anything, but takes but I suppose because of his whole theory became so complicated, and then started to combine gravity and unify that aspect, that it does start to become a big deal, at that point. So that's pretty cool. But it's only at that point that I think that it starts to become a massive deal.
Problem. It became too mathematical. So I think
that's right. Didn't Einstein say that he stopped understanding his theory when the mathematicians got involved?
Yeah,
that was Einstein. Well, I think Einstein actually. Some people have pointed to writings he did towards his death, and he was like, "You cannot rule out the ether," and he started to bring the ether back. And other people were suggesting, "Well, you have this space-time thing, and is that not just the ether?" But I don't think that's really correct, because it is. I mean, space-time is a bit of a weird animal, isn't it? It's space, time, so it's not like. You can't just equate that with the ether and, go to bed or whatever.
I wish he had done more like speed time, instead of space time. If he had done speed time or velocity time, I think it would have made more sense, because then space is what space is. Then what we say, either the velocity can change or the time can change, but the space is constant, But the question of expanding universe, things like that, how do you explain? So it is a complex thing where everything starts changing. How do you do? So it's like a restricting so that we can do the mathematics of the physics. So that's what I'll point out later. The mathematics apply constraints, where physics applies a restriction, and I'm showing you why that is necessary as we go down. So I just want to give a couple of comments and then I'll move on
Yeah, absolutely.
to a thing. Yeah. I mean, the MRE also is proving falsifying Einstein things like that because of the quantum aspects, So
Yeah, I mean,
we will
yeah.
prove that. Yeah. Okay.
What were you? Yeah, you were saying something there about space and time. Time could distance could stay the same, but time and or the speed
Time
and
can change or the speed can change, right?
yeah. Well, wasn't it? Minkowski was the guy who kind of linked space and time.
Yeah, exactly.
They did some strange stuff, though. I mean, like when you're working with space, it becomes just a flat plane, doesn't it? And then time is in the next z-axis, and then you can take like I think you can take Euclidean distances in space. So surveying. So it's a bit of it's an odd concept, but it seems to work in it's like logically consistent within its own framework. So there's nothing wrong with that. But I suppose there are people who criticize it now, Unzicker, but yeah. So go on there.
So essentially, then time actually, because the topology. Now we are talking about topology like toroids, things like that, space and time, but a manifold type of thing. But the time, in terms of tensor, the time becomes a fourth order or fourth rank system, right? Order or the rank 4. Like you mentioned, I think.
Are you saying that the time has rank 4?
Yeah. So I'll put it.
But isn't time supposed to be just like one-dimensional? But then you have these 3 other components: global, local, and different types of time. So this part of the discontinuity idea. Okay.
So rank 4 tensor, that's how we get this one, right? So
okay. Yeah.
Okay. So now so essentially this is where our thing starts.
Can you like explain some of the the subscripts and the I see mu, what is that? You've got so those are the indices on after. So that is a rank 2 tensor, isn't it? If it's you see
eventually it becomes rank 2. This is a rank 4.
Oh yeah.
When you multiply by this one, it becomes it reduces, the rank reduces, and then we can convert it, because we are doing the absolute values, right? The absolute values and normalizing. When you do absolute values, you can reduce the rank of the tensor, right?
So is mu nu, and you have upper and lower indices, and then IPG, IPOR.
Oh, the mu. So this explains about the proper time, and also
how is that described
this
there?
Is the time, it's real time.
Oh, okay.
PR is the proper
difference.
Time, and R is the real time.
Excuse me, those are 2 rank 4 matrices or tensors.
Yeah. So proper time is where you start from. The starting point is the proper time. Okay. The ending time is the real time.
So you know when you're talking about a space-like and time-like, does that come into this? These are all, well, first of all, what do you mean by that?
Okay, when you go to Planck level, right, quantum level, you cannot really talk about space and time. When you go to quantum level, you cannot really talk about space and time, because they don't.
Go on.
Yeah, they don't have a real existence like we do, but so they are like space-like in the sense that you cannot actually measure that space. When you go Planck level or sub-Planck level, you cannot measure the space, and the space may not exist. That's what people are saying. They all they all what you call collapse to something, you know. Uh, we don't know what it may be all intertwined, is maybe like a big what you call the coiled up
Network.
dimension, coiled up
Yeah.
dimension.
Oh, that's true. Yeah. Okay.
So the
Yeah. Yeah.
string theory says that. String theory says that. That's where you have a lot of dimensions in string theory, because when you go into that level, it's all coiled up
Okay.
dimensions.
Yeah. So how does that relate to space-like and time-like?
Yeah. So there
Oh,
you cannot really
yeah.
talk about real space or time. So it's space like because you can even move within that, right? Within the Planck level, it can still move. The particles or entities that exist can move. That movement is uh, in space like it can move, and time like means, you know, it can move. You can say a starting point, ending point. So the events happen, it marks the time. So that's the time, like you have a starting time and then you have a later time, you can still clock it, you
Hi,
can
sir,
still.
from late.
Hey, how
Hi,
are you?
Christopher, nice to see you.
No, Christian.
Yeah, so
I'm
we
not
are
sure.
just
No. So
yeah,
yeah. Okay.
yeah, we
So
are
we're just
just
discussing the
yeah,
difference between time-like and space-like. And by the sounds of it, Rajan, they sound fairly intertwined, obviously, in your definition, which would make sense, right? I mean, if it's
yeah,
space-time, then
yeah,
even when you're talking about space, you're still talking about time to some degree, and the opposite is true. So that's why it's space-like. Is that
yeah,
the reason?
yeah,
So in your core
yeah,
vector, ordinarily
because
you'd have one of the tens or one of the entries maybe in this core vector would be time, and the other three are space, and they're all sort of dependent on one another and interlinked. So three of them would be space-like, and one of them is time-like.
yeah,
Is that a good way to define it? But there's
yes,
possibly more
but
that in terms of world
exactly,
lines as well, right? So you could have a world
yeah,
line that is space-like and one that's time-like.
yeah. So what happens is that transforms, you remember I told you there is a 20-page derivation. I
Yeah.
convert all of the space into time. That's how I get this 4-vector time.
So now
So
it is right. So now it's no longer space is no longer involved. All
no,
right.
but yeah, I only worry about the time domain. I can convert everything to time domain with that transform that
Okay.
I did it.
Pretty
So
cool.
now I
I like.
can talk about rank 4, time tensor,
Yeah. So
everything
you
in
could do
terms
the
of
opposite. Could
time.
you could convert them all into space as well?
Yeah, and then you can convert it. There is a conversion from time to, with the transform you can convert back to inverse transform. You can do inverse transform, convert the time back into space and time.
So yeah, you could convert right. You could convert the time into space, and then you'd have a 4 spatial vector, essentially.
Yes.
Right. That's most of
Yeah,
my
you
work
can
is
take it to
based
4
on just
spatial
four,
vector as
four
well.
spatial dimensions,
Yeah,
which is fine.
yeah,
But I don't really propose to understand it. I mean, there might be more to that. Obviously, I think the 4th dimension is pretty weird in terms of trying to differentiate
oh yeah,
over it and other things like that. So
yeah, topology.
yeah.
But in order to get geometry you may need that. In order to get your geometry, eventually you may have to convert it back to space to get what the geometry is, to understand what the geometry is.
Okay.
So that's at a later time, but it's easier to manipulate with time. The rank 4 tensor of time, you can manipulate that, and once you get a result, then you can convert it to space. Because when you talk about space and time, they get so messed up. You have to talk about mass, which is again a difficult thing to talk about, because when you talk about space you have to talk about mass. And you have missing mass problem, the dark matter, all kinds of things come into picture. It becomes totally a total confusion, of sorts. And then you assume things there, which again is going to throw everything out the, bucket, so to say. So that's why I want to just, that with the transform I have showed that that precisely showed in a way that everything is like a black box, but we can think of time, and you can now concentrate on time domain, clock, how the clock works, things like that. So that's what I am trying to do here. So this is the logic. Okay, this is the logic, and I can say this one is, I can use like what Gerd was using, like a switching circuit. A switching circuit, the time is actually on and off, right? You are switching events, you can convert into on and off. So you can convert the time into switches. So you have switching circuit. The time is like a clock. Clock is like a switching circuit that it keeps ticking forward, and we can yeah, we can show. I showed you in one of the things how you can simplify by a simple experiment, that group velocity and things like that. Um, I believe the fast radio bus that we see, right? That people try to explain the signals that
the group velocity of the wave function, is it? I was asking earlier.
Yeah, the group velocity of, let's say there's light and sound, right? What is the group velocity of both of them together? If you put light and sound together, what is the combined field? What is the group velocity of that unified field?
That's kind of going back to your research, but you know the way they talk about group velocity a lot, just in general, are they usually talking about like you say,
particles,
sound, and they're talking more about particles, which are
particles, like you have muons, electrons, all kinds of particles, right, in the mix quarks, and then they have individual velocities or phase velocities, but also velocity. The whole set of particles come together. Like a neutron, for example, has both electrons and protons together, right? And the group velocity may be referred to a neutron, but it has a phase velocity of proton and a phase velocity of electron, right?
Protons and neutrons make up the nucleus, well, of the atom.
Yeah, the nucleus. If the neutron is traveling, can the neutron travel faster than electron or proton, or will it be less than the proton and the neutron? That's the whole question. And I think depends on the medium. If it's a normal medium, I would think a neutron will be slower than either electron or positron. That's what I think, a phase velocity. And
heavier, is it? Or, well, one of them is heavier. Depends on what kind of neutron, down or up. I think they're also.
Yeah. So those chirality comes into picture again.
Or, yeah, I mean, it would be down. You have a down neutron? No, actually, I'll have to look that up. Yeah. I might be getting confused there. Sorry, go ahead.
Rajan, in my model, there would be, due to the exactness of the charge, no difference between a proton and an electron and a neutron from the charge point of view, but there would be from binding energy. Otherwise, the neutron would be the same like an uncharged proton. So when you combine the charges of a proton, which would be essentially the mass of a proton plus the charge of an electron and a positron, which would annihilate itself when there are free particles and an accelerator shot on each other, and then they give this 1022 mega electron volt or something. But inside the core of a massive particle like the proton, which we don't know what it is.
Yeah.
From experimental point of view, we see things like mesons exist for a very short time frame and these kind of things, but they are not real. They could be man-made in the accelerator. They could all be just measurement artifacts of our own energy putting in the space-time by the accelerator. What is real, I think, is charge. And charge in a medium like we all think could be a transport reason for superluminal basis effects in gravity or possibly even beyond.
Yeah.
it would not mean that these effects would have a balanced mass inside proton. So when you have a proton, something is positive charged. If you think the positive charge is exactly the same than a positron, then you need to be able to calculate one way or another the binding energy, because then you have some kind of bonds between the positron and possibly they're either space-time, then it's a direct reaction, but when you put an electron in the shell of a normal atom, then you get a normal orbital thing like QED. Yeah, this is simple. But what if it is possible to get into a range near the core, so below 10 to the power of minus 15 meters, when you have the hierarchy of alpha, you see that there is the Bohr radius, and when you divide the Bohr radius by the multiply the Bohr radius with the fine structure constant, you get exactly in between the Bohr radius and the classical electron radius. When you multiply a second time, you get to the classical electron radius, which many physicists think it's unphysical, but I think it's very physical. And then it would be, just by logic, it would make sense, especially from the three-dimensional aspect of space. Multiply a third time, then you would get to the 10 to the power of minus 15, 16, 17, 18, minus 18 meters. And the rules, which then by 10 to the power of minus 15 could be another subspace bubble where these energies were not repulsive anymore, but attractive. And this is what looks like gluons then, but actually it's not gluons. It's, for example, two positrons and one electron in a dance, which look like gluons. And then you would have these U and D quarks effect in what you measure, because you think you need gluons to have them. But in effect, it would be a box in space-time, which is quite rigid. It is an ice-space box, which keeps these standing waves in control.
Yeah, that was my confusion there. I was saying that, so in a proton, you have, like, let's say 2 up quarks and a down, and in a neutron, it's 2 down and an up. Or it might be the other way around.
Yeah, so what I'm saying is this could all be just voluntarily. When you look just at the charges are exact to the power of 22. That can never be accidental. So one must assume the reason for a charge is the same in the proton than in the electron. The electron is such a tiny particle which has the ability to jump around, if you want, in the shells, logical shells, the distances of the QED rules of the atom, but the atom is about 65,000 times smaller in the core, away from all that, and cannot really affect that rule. So all these rules are somehow mathematical or structural by, well, some either exactness of ice-space or the exactness of some mathematical rules, even if it is virtual particles. I don't believe in that, but I will not exclude it that there is something to it. But whatever is the mechanism, it must be exact to 10 to the power of minus 22. And that is shockingly precise. That would perfectly fit to ice-space only. There can no other theory who can predict 10 to the power of minus 22 anything, because you can only measure up to 10 to the power of 14 or something. But by nature of exactness, ice-space predicts that, and that means if we see charge, then the value golden ratio for the charge in the electron, for sure, due to the simplicity of the equations, must be the same golden ratio in the core. But when golden ratio is a distance of a moving flight particle, or whatever Rajan would mean it with his time calculations, or I'm not sure what is the length reduction, or if that is relativistic, what he's calculating there. Rajan, I ask you later if you want about the details of what I'm up to here. But it is essentially golden ratio. So when golden ratio to ratio of 1 would be a force, that would in one way or another need something to be calculated up to the proton mass. And when you then want a neutron, you would add an electron, but the electron masses and the neutron proton masses do not just subtract. They have binding energies. And these binding energies are notoriously difficult to complicate, to calculate. they are differential equations. So when they are nonlinear, highly nonlinear, and they can be calculated by some standard means of QED and other stuff, but they are all approximations. No one knows what the exact mechanism is geometrically. And when I know I have a quantum of time of 1/6961 exact, and golden ratio as a charge factor exact, I must assume that this is also holds in a proton distance range. So 10 to the power of minus 15 meters, essentially, as the hull of the proton or neutron, whatever that is, or the hull of the space keeping the forces of the proton in a box. Let's call it this way.
Yeah,
I don't think that proton exists. It is not a particle like a Lego piece. It is something which is assembled, and inside of that assembled box, it is very, very dynamic. If it is relativistic inside, that is the question. Then these kind of equations and things which Rajan discusses here apply. But if the things would be exact, then they cannot apply, because I-space cannot be bent by relativity. If a Lego piece doesn't change its size when you bend it in any way.
Okay, but don't you have? So you accept then that there is structure inside the proton. So would you agree with the quark model?
I suggest there is structure in the proton, and I suggest it is the same what we see in the mathematical equations of the I-space for the electron, which are unbelievably simple, yet extremely precise up to the last measurement digits. If we believe that cannot be accidental, then we would believe the geometry is real, what the I-space sees here. If we do that, then we must assume that in the proton and neutron, the same logic behaves, and there cannot be just a positive charged proton be happy with having dances with an electron. It is much more likely that then you have accelerated electrons and positrons in a box, which give, due to their acceleration mass, the dynamic mass of the different core particles, proton, neutron. But they would be multiples of integers times geometric factors. They cannot be anything else.
Okay.
The interesting question is there a kind of relativistic effect inside that? Why would we measure that neutron and proton as a box particle, which is quite rigid? And the answer is, would the movement of the particle inside this box be superluminal, you would measure it even rigid.
Okay. So yeah, so then this, but yeah, if the particle inside is doing something different to, let's say, a normal positron or electron outside, then could we redescribe that as a new particle in a sense?
This is, I'm not sure. So the question is it a form of space? So that what the particle looks like could be a structural recipe for space. But then space is even more fractal than I thought. What I can prove is that I need 6 subdimensions to get the electron right. And we only have C3 dimensions, which are both string theory and I-space theory, for more or less coincidental reasons, think we have more than 3 space and 1 time dimension. That is still compatible to Albert, because Albert never had anything to do with subspaces. So as long as you place the subspaces in coordinates which Albert could calculate, then everything is compatible.
Yeah.
It doesn't matter if you calculate to an infinite mathematical dot or to a non-mathematical dot with a finite extension, as long as the results are right, what get out of your equation. That is compatible. But what is not compatible is the idea that you can, in pure 3-dimension plus time, accelerate something and it gains weight. Because why would it?
Yeah.
When you accelerate the box, then anything of type inertia will resist this movement. And we know that from dozens of experiments in a very precise way.
Right.
So when something very fast, even light, is in a box and you move the box has weight to move.
Right. But there are people who dispute the mass increase of a moving object. I think at Fermi,
yes, and so I do, because what is actually increasing? This is my question. I'm not disputing that the effect is measurable in the way the Einstein believers do that.
Well,
and I do not criticize Einstein at all. I'm very fond of Einstein and think this is more correct what he did than that what quantum mechanics showed. On the other hand, quantum mechanics is experimentally verified in a very convincing way.
Yeah.
And
but
it's just
Einstein had this thing where, you know, there was uncertainty surrounding this issue because nothing had been up to the speeds necessary. So, for instance, an object accelerating towards the speed of light could never reach it because it would get heavier, or because time would slow down to the point that it would never get to the speed that it needed to be at. So there were these two.
There are a couple of questions. When you accelerate something, the standard theory of relativity says you can accelerate it infinitely long, and it will get heavier and heavier and heavier. And there are derivated papers of Einstein there who says there is an upper limit to the maximum mass you can gain with that, for good reasons. In these papers, I read these papers. I'm not fond or non-informed. I'm not a relativity expert. I just read these papers and said, well, interesting. Could be there is an upper limit to anything, like there's a lower limit to anything. Otherwise, we wouldn't have Planck units, right?
Right. Yeah, but so when you're going, but you could also look at it that the reason why you couldn't reach light speed is because time slows down, and then because of that, you'll never reach the speed. I think so. There were these two different camps, and both of them have been trying to prove one way or the other which is true. And I think at Fermilab they did some tests where they could find no mass increase even when particles were going very close to the speed of light. I have no idea.
Really? No mass increase in an experiment close to the speed of light?
Yeah, this is what. So their interpretation is that the time is slowing down, and that is why matter can't go to the speed of light.
Okay, this is what I really cannot follow. Any theory who says that the time itself, take my word for that, time itself, time is not just the ASCII word of 4 characters,
right?
It's a concept, and without time, you cannot talk about motion.
Yeah, I agree.
So when you don't invent a concept of time, just mentally, be it a thought experiment or real one, doesn't matter, then you have no movement. Everything is frozen. And from a much overlooked point in all of discussions of relativity is that when an atom emits a photon, it does that in 0 time and it absorbs it in 0 time. And while the photon is for millions of years or billions of years even in flight, when it is emitted 13.7 billion years ago and we receive it in our detectors as a very old photon today, it traveled that journey for that time, but for the photon, it was as if it was just jumped from the location where it was to the location where Earth and its detectors are now. Do you know what I mean?
Yeah, I follow you. But that doesn't that kind of aren't you therefore justifying what, like, the Fermilab interpretation there, because you're saying, well, there is speed with
good. Back to the Fermilab. So when Fermilab says the time itself stretched, that would mean a clock of any type, not just atomic type. That was always the argument of Einstein. It doesn't matter what your clock is composed of. Time itself slows down.
Yeah.
And I don't think so. What happens is length contracts. Time is not slowing down because I see the quantum of time that is ticking. And quantum of time cannot be contracted or expanded. This is Lego.
But isn't space also made of Lego, and if space is contracting?
No, because there is an effect in space-time, not in space. Space cannot contract. This is also Lego, but space-time can contract. When the movements between Lego positions take a shorter or longer time from A to B over n pixels. So the pixels in space in I-space theory are not the same size and granularity than pixels in the Lego arena where the constants of nature come from, obviously. So the constants of nature pixels are like Lego Duplo. They are super pixels and they can be easily seen. Otherwise, we wouldn't have big integers in my equations.
Okay, but then if you have this space-time substrate and that can...
So, and you have Calabi-Yau spaces as an idea where the mechanisms of subspace happen inside, and all Calabi-Yau mechanisms make up our universe and what we do here.
Space-time part, you have this space-time substrate, and that can contract and expand, and the time in that is changing, yeah? but only
no, it's not. The length is changing, which is the same.
But if time is part of that system, and that's all, are you saying?
But how could it? Think of it. Is an imaginary unit in the root of the x squared plus y squared plus z squared minus t squared. I would be with all these Einstein followers if the time would go plus t squared and would say, yes, we have a time dimension, everything is symmetric, everything is fine, and there is no difference between time and length. But it's just, it cannot be far more from the truth than it is. It is root of x squared plus y squared plus z squared minus c squared times t squared. So first of all, the time is multiplied with the speed of light squared in this equation and has in its own a complete different mechanics. So why is this multiplication with c squared necessary?
Well, that's Poincaré's work again. He came up with that four-dimensional. There's kind of that time was this imaginary unit, fourth dimension. It was part of his work. So that's why it's squared, I think, in order to make it real.
It is squared because only when you multiply it with c squared, you get the right equations and results which you experimentally verify out of your Maxwell equations.
Well, yeah, but I think
there is no other reason except that the Maxwell equations are completely wrong when you don't do that.
But I think Poincaré had like 3 real dimensions, 1 imaginary dimension, which was time. And so I'm just guessing in order.
You can say it this way, but would it change a thing from a logic? So when I say we have movements and the time is the same and is discrete and is always a tick, which is like a binary clock in a computer, then either your physical speed needs to be slower or faster of that what you perceive as a movement. But what is a movement? A movement are 2 photographs in time measured by a distance in pixels. This is all we can do. All our measurement instruments are discrete one way or another. They are not complex numbered. They are not imaginary. They are nothing. They are atom-based and atoms can be counted.
An absolute time reference then, a bit like Newton's absolute space.
Yes, so this is what I'm saying, but this doesn't negotiate in any way that relativity is wrong. What I'm saying is the interpretation of relativistic people who are experts in the field, that time is a wobbling thing is completely wrong in my opinion. It is exactly the opposite.
It's be relative. So like when you're on the spaceship moving at a certain speed, time is going normally from your perspective. But from outside,
and for every contender in the universe, whatever his relative speed is relative to one other, the effects are effects of measurement.
But you would be, yeah, you'd be on the spacecraft, and time would move. Like you would see no effect. You know, in terms of like
look, when you do a simple experiment, do you know the relativity experiments in Garching? They do that every year. Maybe you have time to come to Munich and have a look on them themselves. They are extremely expressive.
Yes.
And they show you that they have an atomic clock with, I think, 16 or 17 digits after the comma.
Yeah.
And they are 10 meters away, apart from each other in the lab. And they get synchronized by a button in the center with the exact same cable length to the 5 meters left and 5 meters right clock. And the clock's running in sync. So you can literally see that when they talk and explain the experiment, they show you how it runs. Then they press a stop button for the sake, and you see after, say, 3 minutes of talking, the clocks up to the last digit show the exact same integer digit in the 16, 17 digits clock when not moved. Yeah. And they do the same experiment again by shifting the right clock 20 centimeters up by a mechanism on where it's positioned. And then they do it the same. They measure 3 minutes, and then you can see that after these 3 minutes, the clock, which is higher up out of the gravitational field of Earth, is deviating from the left clock.
Okay, right. Well, that seems
so sensible. Is that what we perceive as a change of time?
Yes.
And I'm not in any way arguing this is not happening. There are people who say complete relativity is nonsense, and so this is not at all what I want to express here. To get me right, please. Yeah. Sure, I said all these experiments show exactly the right things, are possibly more precise than the quantum electrodynamic experiments, and G-2 experiments always claim they are the most precise, but I don't think so. So these relativity experiments are the most precise in the world because they show a atomic clock with 16 digits after the comma to be out of sync when 20 centimeters height is between them changed for 3 minutes. This is crazy complex. This is so precise. I cannot think of any more precise experiment. Now, it's all about the interpretation of that experiment. What have we actually seen? The clock has moved 20 centimeters higher out of the gravitational field of the Earth.
Yeah, it's
of the average gravitational field of the Earth. But what is the average gravitational field of the Earth? Let's assume for a moment that the Earth would be a neutron star, and the neutron star's core would be sitting at the same distance of the center of the Earth, and we would be in a spaceship at the orbit around the neutron star in a fixed geostationary position by some techniques or whatever. We would just assume we could do that. And then we would have the same gravity, just very, very precise. There would be no mountains and anything because the neutron star would be a perfect bowl.
Yeah.
So we would have no irregular effects of gravity, like Himalaya. When you fly with a satellite over Himalaya, you get gravity effects because the mountain is there and it pulls the satellite down. When you fly over the sea, it doesn't pull the satellite down, except for the water weights more than, but that is a density thing. So you know what I mean? You have some densities.
Yeah.
And
okay, yeah, I get you, yeah.
Relativity has a lot of corrections. This is the most problem in relativity. It is a lot of corrections for a lot of things.
Yeah.
You have redshift correction. When light escapes, you have the redshift which you need to correct because you're leaving a gravitational field, which gets weaker with distance. You have the acceleration, and the acceleration means that when you fire a rocket up, then you need its special relativistic effect in flight direction, which subtracts from that redshift. It's another effect. And when you're in orbit, all these three effects doesn't compensate. So they are a balance depending on where you are.
Okay, yeah.
So this is not so easy to say what you actually measure when you do relativity subtractions.
Yeah, well, this is it. I mean, you could even, some people have argued that the fact that a clock, let's say, in space runs slower than on the Earth could be to do with like pressure density, especially with something like as sensitive as an atomic clock. If it's got like the pressure of the atmosphere, you move it up a bit, that slight difference could affect the ticking.
But the clock in space would run faster, not slower.
But that is correct. That's what it's meant to do, isn't it? The closer you are to the Earth, the slower.
The closer you're to the Mars, the slower you will run. Yeah.
Closer to the Earth, slower.
Closer to the Mars. But
what? Sorry, what?
Closer to the Mars will slow your clock.
Obviously. Yeah. So if you're in space and there's less like the theory, like one of the concepts someone came up with is like less pressure on the clock.
Yeah, but first of all, there is equivalence principle, and the equivalence principle of Einstein might not necessarily be correct under all circumstances.
Yeah, maybe, but well, I mean, I'm just saying, you know, you'd have to factor these things in. But I believe that they did do experiments where they totally sealed the atomic clocks and made sure that pressure of atmosphere wasn't a problem or vibration or any of these, and they tend to get the same results. But yeah, so I mean, it's plausible. But anyway, that's all kind of goes to my point, where to Fermilab's research that time dilation is a thing, right? Isn't it?
I know just the experiments from CERN because Walter, my professor who taught me on the standard mathematics and results of quantum mechanics and relativity in an overview course, let's put it this way, told me what they actually measure, which means not what you believe in your equation is what is correct, what this is interpretation, but what do you actually measure? And when you measure a speed, you need think on a car. There are a lot of ways you can measure the speed of a car. You can sit inside the car, look on your tachometer, and think you know your speed of your car.
Sure.
Because it shows you. But how does it know the speed? It knows the speed, or think it knows the speed, because it's on wheels. But if your wheels have 8 mm profile in the beginning, And even if you have perfectly mounted them and you're on 7 millimeters, then the wheels rotate faster than they should because they have a shorter way per revolution with a less profile, and they show you a higher speed, which you don't have. So you cannot measure the speed of a car this way in a car, because otherwise you would have to calibrate against your profile. It's just one thing. When you measure it like a police from the external, you could think you hit a laser beam horizontal once and an exit laser beam horizontal twice under a distance of exactly 1 meter, whatever that is.
Yeah.
Let's say it's calibrated, or 10 meters for more precision, and then divide by 10. Then you have the start-stop stuff. That seems to be very precise, right? But the light will need from the sensor is a photon. Even if a single photon measures you in a theory, it needs to the mirror and back to reflect with you, and then the next time. So this is not a Heisenberg uncertainty which you get here as unsharpness. This is an inherent unsharpness, because when the photon is back, your car is already moved over the line. There is no mechanism which tells you instantly that you hit a certain fence line, even a virtual one.
Right, but it's
measurement per se, not Heisenberg, but measurement per se changes your position before you are done with your measurement. And
yeah, but for the purposes of like something like that, it's probably pretty accurate.
Yeah, but all the models idealize the concepts and think it is precise, but it's not.
Nearly.
You can't even measure it with that precision.
I mean, it's precise for like all intents and purposes, I guess. But
I don't think so. I don't think so.
What does it have to do with the light, the time issue?
I mean, every measurement in the world of length has been moved to a counter by counting times, because length measurements are notoriously difficult to do, whereas time measurements are comparatively simple to do in labs. So we take frequency counters, we calibrate them by means of whatever, Kodata Labs, whatever the measurement manufacturer is doing there, calibrate against the normals, and then say, we know now what 1 second is, we know now what 1 meter is with an uncertainty of x, or plus x minus epsilon, whatever, if that is not symmetric.
Okay, well, what about, should we get back to Rajan's thing here? I think you were going to ask a question, Christian, about the time metric, or it was somehow related.
Yes, sorry. Actually, what I wanted to see is, if that what Rajan calculates there, is it a space, is it a subspace, or so what kind of relativistic mechanisms apply to that space in that mathematical format? Because in integer space of I space, it couldn't apply, because Lego cannot be bent. But when positions of Lego relative to other positions of other Lego would move in hyperspace, or call it whatever you want, 3D normal space, which we perceive, then it could be calculated with normal relativistic equations, or it must be even.
Yeah.
Actually, there is no non-relativistic speed. People always say that when you in the edge you have Newtonian compatibility and so on. Also, that is not strictly true. When you look deeper, even the slowest movement will change your time, because the slowest movement will have a relativistic effect at a certain comma position after the digit. There is not something that you need 2/3 of the speed of light to see something. It's just not true. In a virtual I-space experiment, I see any such movements because I have 42 digit precision, or 100 digit precision if I want. I can change that in Mathematica. So there is no movement under non-relativistic conditions. And this means, how can it be that movement changes mass?
Yeah. So once I was teaching physics at school level, I found out a way, connection between classical, relativistic, and quantum, why they came into being. See, Newton thing, classical mechanics, all fine. Galileo and Newton thing was all fine. But the question is, when objects move, there's energy involved. So is it energy absorbed by the object, or is it dissipated to the surroundings? So that's the question. When a mass is moving, the mass can absorb the energy and then keep moving, or it can actually give away, like heat. It can actually dissipate. I think that's where the quantum mechanics looks at one point. The relativity says that whatever the energy, it absorbs that, and then it converts to, especially at the particle level, the energy converts to mass, because the particle level is easy. Mass and energy are equivalent, which just a square.
But this is one word I don't buy into. It is not equal. The mass energy equivalence for rest mass I buy. That is extremely precise and visible in iSpace how it happens. It is extremely precise. Otherwise, I wouldn't be able to calculate constants of nature. But the PC squared, so it's not E is MC squared. Is E squared is MC squared times plus PC squared.
Momentum or something.
Yeah, but the momentum is an addition in this equation. There's a plus sign.
Yeah.
So
that's
that is all about, is that a valid plus sign? Is that allowed to say so? And the answer is yes and no. Yes, if you buy into the equivalence principle of Einstein. So if you buy into the equivalence principle, then the plus sign is allowed. But I don't buy into that.
Yeah.
Because it would involve a continuum, a hypothetical continuum. And if you have a single pixel somewhere, you can't have that plus sign anymore, because it would be a violation of conservation of energy. And I believe in conservation of energy. Boy, do I believe in conservation of energy, up to 42 pixels, digits. And that's why that doesn't fit together. Relativity and quantum mechanics don't fit together, because it's all about how do you conserve energy 20 digits after the comma when you everything wibble, wobble, bend it around as you see fit. Otherwise, your equations on cosmology are wrong. And here I would step a little bit back and say, yes, all of cosmology is wrong. No problem here.
You're probably right.
So that's a good question. What I'm saying is that I'm not defending one or the other from a relativistic perspective. If you look at a relativistic perspective, what Einstein looked at it, all I'm describing is what he was looking at it, is that the energy is absorbed like a proton or electron. As it moves, the kinetic energy is absorbed, and this energy becomes mass, so it increases the mass. That's the perspective of the relativistic.
So you're saying an atom absorbs a photon and gains the impulse by the photon, or its energy?
Let's say an electron, right? Just look at the electron. Electron is starting to move, right? So it has a rest mass, but it moves. It has a kinetic energy, right?
Yeah.
Due to its impulse.
Yeah, impulse. So that kinetic energy is absorbed by the electron. As it
is gained by the electron due to its acceleration. But what accelerated it? Normally, you can accelerate electrons only in curves. You cannot accelerate them straight easily. And linear accelerators you can. But what you mean with it loses energy is probably what is called Bremsstrahlung. So when you have a circular accelerator, necessarily all magnetic fields are pseudo-curved. They are, in a way, centered on a pseudo-linear calibrated thing, grouped until the next such section comes. But the thing is not really a curve. It is an n-gon, something like, geometrically. So it is, when you have 1,000 magnets, then you have 1,000 gon geometrically. So a circle which is quantized in 1,000 plane roots which accelerate from point to point and bend the electron at the point where the magnets are placed mechanically.
Yeah.
Because you cannot have a magnetic field which is a true curve. This is just an illusion. This is just nonsense. Your hardware you build is has an extension. Yeah. So your magnet has a length. Let's say the magnet might be 5 meters long, and in that 5 meters, it is accelerating the electron and at the same time bending it a little bit before emission, so that it stays within the curve they want it to have. Now, when the first round of the electron in the accelerator is gone, the impulse has increased. The thing has accelerated, let's say, to 0.1 C. And then you need to increase the magnetic field, because if you don't increase the magnetic field after the first revolution, the particle will hit the wall of the accelerator. Then after, say, 1,000 revolution, it has 0.5 C. After 10,000 revolution, it might have 0.9 C. And after 1,000,000 revolution, it might have 0.99 C. But all these revolutions will have a feedback loop with increased magnetic field strength. Otherwise, the particle would not stay in this curve. And while you do that, all the energy you pump in, the electron emits as Bremsstrahlung. But is that Bremsstrahlung real?
What does the word mean? Sorry.
Sorry, the German word for Bremsstrahlung is the radiation which emits from the, I don't know the English word, I'm sorry. This is the radiation you get from a curved charged particle in an accelerated curve. If you enforce a charged particle in a curve, it emits light. It doesn't like that. Yeah?
That's right.
It takes the energy from your magnetic acceleration, but the price is it emits a lot of light because it cries under this acceleration. It doesn't like it. In a linear accelerator, this doesn't happen.
Yeah, okay.
This does not happen, okay? In a linear accelerator, the electron has no problem getting accelerated linearly. But why is that?
Yeah. Sounds like some sort of relativistic effect.
Suppose we have a cathode ray, like a cathode ray, right? Like a cathode ray tube, just a linear thing. So you have the potential difference. What is driving the electron is a potential. You have a cathode and an anode, right? Yeah. So the potential difference between the cathode and anode is driving the electron from one to another, from cathode to the anode. It is just pulling the electron. So electron is getting accelerated as it goes along. It has a rest mass, but when it is accelerated, now it has momentum. That momentum gives a kinetic energy. The relativity says that, I mean, I'm just saying relativity perspective, that energy is absorbed by the electron and it increases its mass. That's a relativity perspective. I'm not saying it's correct or wrong. That's one of the relativity perspectives.
Roger, in my picture, I'm not saying the electron gains this mass or is absorbing it. In my picture, the space around the electron, which moves with the electron, is gaining the mass. The electron is not changed at all.
Yeah, so
the effect is the same, but actually, in my picture, in iSpace picture, you accelerate subspaces because you cannot accelerate particles because particles do not exist. Particles are just light. And light moves with the speed of light in a box with mirrors.
Yeah.
And that is all you need to perceive mass.
That's fair enough.
Yeah, that's iSpace perspective. I'm saying that.
Yeah.
So you look at the three different things. I'm not saying which one is correct right now. I'm saying that I'm just looking at each perspective and what it's saying. Yeah. And then you look at like iSpace perspective. You talk about subspace, but the relativity does not talk about subspace or anything like that. So, and the quantum mechanics looks a totally different way. Quantum mechanics says that this energy is dissipated, right? So now you have dissipation and the entropy is increasing. So the quantum mechanics looks at it totally different way. It doesn't say it doesn't say that the electron is gaining mass, but instead the energy is dissipated and it could emit light, things like that. So the quantum mechanics is right from that perspective of the fact that it emits light. When the electron is moving, it may be emitting some light, may be correct.
Yeah, but you're talking about the circular movement now. It is not emitting light.
The linear thing, it may not happen. See, that's the problem. So linear thing, the relativity may be closer, but your iSpace is may
Yeah,
question
but
that.
isn't it a fair, interesting question? What geometric effect the curving in its own? I mean, think on a magnetic field, what it is in a permanent magnet. So is a field which you can see by iron powder even. You can see that field. This is a
Yeah.
simple experiment anyone can do.
Yeah.
And why would a truly curved field like this, with visualized by quantized iron powder, by iron particles are quantized, move in curved passing through the magnetic field, emit light, while a straight passing through that field? So can a light move through a permanent magnet field in a straight way? Because there is no straight field line, not a single one. How can it be? Something doesn't get together with all these theories in quantum electrodynamics.
Well, what about the issue of kinetic energy then? I mean, isn't that it's equal to 1/2 times the mass times the velocity squared?
This is the next good question. If you talk about the papers of what was his name? Van Bell, John-Louis Van Bell. If you haven't read them, they are really not entertaining. But he is reviewing Feynman basically, not Einstein. He's also, of course, hitting Einstein where necessary. But he in depth had reviewed the Feynman books, and I know him for 12 years now. Okay. Way before ResearchGate came, way before anything. So he made himself, he is not a physicist like me, he is an expert in economics, but the differential equation in economics are exactly the same than the differential equation in physics. Isn't that funny? Yeah.
Yeah. Right.
So he understood the differential equations for physics better as an economist than most of the relativists and quantum mechanics experts do. And then he didn't believe anything Feynman said, because Feynman was on God level and said, yeah, Feynman cannot make a mistake, and said, I don't believe anything, I recalculate the book. So he recalculated all these three Feynman level 1, level 2, and level 3 volumes and found that he was not always right.
Right.
And one of the interesting parts is the Stern-Gerlach experiment, where he make a logical interpretation error in what would happen when you have two Stern-Gerlachs behind each other.
Right.
Where you have in the end a particle moved by 90 degrees and change the phase. And he could prove mathematically that the phases don't change in this. So you measure nothing with this experiment. Not because quantum mechanics is correct, but whatever you calculate will be zero effect in this kind of setup. And Feynman.
Well, generally the phase is irrelevant, isn't it, to spin?
Yeah, only the phase is relevant. But if you mock up your experiment the right way, then the phase is subtract by your experimental design.
Well,
and then you measure nothing.
This Stern-Gerlach experiment is measuring spin, and as far as I know, the phase is irrelevant in those calculations.
Oh, it is. Of course it is. Any measurement, quantum mechanics is all about the phase. It's just look at the Feynman books, and you understand how it works. You have your clock, and you make your little arrows, and you add up your little arrows, like in the simple book for beginners, and you get the correct equation of mass. You get the correct. So everything of the equation of quantum mechanics, like Feynman books, works perfectly at first sight.
But I think the Stern-Gerlach experiment is measuring spin, so it goes through one magnetic field, inhomogeneous magnetic.
It measures
field.
electron spin, yes, in an inhomogeneous magnetic field.
So it's not looking at phase; it's looking at spins.
But you can't measure spin without looking at phase. The calculations always involve phase.
But if you look at the phase and the spin, the phase is irrelevant for the spin. You can just leave it out. You can just
no, you have an electron. This is not light, where you just.
No, I'm pretty sure. I mean, I could look into it again. Of course, maybe I made an error, but definitely in light, it's irrelevant. Like polarized light, phase doesn't matter.
Yeah, of course, it's relevant in light.
No, it's not relevant. You can leave it out of the equation.
Either I misunderstand what you are talking about, or we have not the same.
Well, yeah. So just to clarify, what I'm talking about is the.
Look, when you do some cosmological equations like this, the couple of world theories, but people with higher reputation would put it this way, then they make these equations a lot of plus signs, but what they actually add up between their plus signs is phases of the same particle. So the one plus sign turns a particle's phase by 30 degrees to the right, the next by 15 degrees to the left, the next 33 degrees to the right. So when they have the right number of factors added up, then they suddenly get the right experimental value which they see in the experiment.
Yeah, I mean,
all they do with their plus signs is not add mass or anything complicated like that. No, they just add phase. What a concept!
Yeah, there is an overlap there. I noticed that Feynman's talking about this spinning thing that goes, and then a certain amount of it is reflected off the surface of a glass, and depending on the thickness of the glass, you get these interference type stress patterns. But
yeah, that is all correct. So that there's nothing wrong. But what I wanted to state is that Van Belle has found the error in one of the pages of where Stern-Gerlach complex form experiment is described, not a simple one with one Stern-Gerlach, but a cascaded Stern-Gerlach, where Stern-Gerlach is another Stern-Gerlach, and then a third one behind. Yeah. And the one makes not the curve, but it makes just two dots, which is the unexpected result of the Stern-Gerlach. Yeah?
You're right. Yeah,
but then you can take these two dots and feed the two dots output as an input in the next Stern-Gerlach.
Right.
When you then turn the Stern-Gerlach by 90 degrees to the right, the second one, you should get a star collection, like a plus sign with 4 dots, but you don't. This is where quantum mechanics plays you a fool. If you think it's naive, you can just, this would be classical, but this is not what it's doing.
Okay. Yeah, but that's still about spin and...
Well, this is just probabilities which you add up there, and these probabilities can be calculated.
If you're looking at the polarization experiments, you have the polarized light going through one filter and then another filter at, let's say, 90 degrees. And if you put one in between at 45 degrees, it's brighter at the other end, you know, so that's unexpected. So but that is the... that's the polarization thing, and phase is not involved in that calculation. And I'm thinking that you know, the Stern-Gerlach experiment is similar in respect to that, in what it's doing. And I'm you know, I'm not certain of
the problem is I lost track. What I wanted to talk to you or state you with the Van Belle's experiments, and that was an important point to our original discussion. I just deviated myself too far from the point where I wanted to be. I'm sorry.
No problem. John Way Van Belle, is it? You were talking
John Way Van Belle, yeah.
You were talking about the curvature of the magnetic field, straight lines. Why isn't it emitting light?
Why? Yeah, exactly. So when you want to see what an electron is doing, then the Feynman equations in book 1, 2, and 3 about quantum mechanics are just right, or should be, to put it this way, because they are really the reference by all means. So any physics professor in the world you talk about says, yeah, that's the reference. That's we trust what's written there, and that's it. Yeah.
Yeah, exactly. No questioning at all. So that can be a
this
problem.
Is always difficult and dangerous, but they never question Feynman's methods. Feynman was a genius in math in the brain. He had not a Mathematica. So anyone with Mathematica today, including me, can do things Feynman did without knowing why that is correct. I don't care. It can calculate that if I want, without understanding it even. It doesn't matter. That's the cool thing. I don't need to learn integration or differentiation or anything. I feed the equation and get a result because Mathematica can handle the physics directly.
Yeah, that's pretty cool. Okay, so... So where are we now in the grand discussion here? I think you were.
It is about what is potential energy. What is that? Is it allowed to say that something which was accelerated gained weight or not, and that falls back one way or another to the equivalence principle, to the second one?
Right.
The first one is undoubtedly correct. Yeah, probably don't need to discuss the basics. So we have energy conservation and that's it. But is the second one just an illusion or not? When you have perceived gained weight by movement, horizontal movement, takes you no energy. It goes on forever if you have no friction. Okay? So the only way to gain or lose something is acceleration or deceleration. When you accelerate, and Einstein is right, would you be on a weight which would magically be able to weight you while you are under movement? You would see that you're heavier. And would you have, say, half the speed of light and decelerate, you would have to lose weight. Now, that can be measured, interestingly, in cosmological scenarios where black holes turn around each other, because not only because of gravitational waves. So with the gravitational LIGO experiments, you can measure these things really in realistic ways, because the theory of relativity is shit exact. It's super precise.
Yeah, I don't know if LIGO is exact, though. I mean, you have these.
It is. LIGO is the most exact experiment on the planet. They can move distances up to 10 to the power of minus 21 meters.
One of the specs on LIGO, I think the wavelength is. I'm just making up numbers here. Let's say it's 500 nanometers.
No, this has nothing to do with the wavelengths. The LIGO is a clever construction in its own to measure length, which would be below the atomic range. People think LIGO cannot work because it's a measurement precision below the atomic range, but they haven't read the LIGO papers, how they do that. This is unbelievably clever what they're doing there.
The thing they're measuring is below the resolution of that wavelength. So, you know.
Yes, and it is still correct.
You know, a truck going by down the road could produce a measurement that looks exactly like.
So it's all about correlations of measurements of two LIGOs at some distance from each other, where the truck is only affecting one and the rest is noise. It's all about how do you detect noise. This is all about LIGO.
They did show, like, I think they were about to pull the funding on LIGO, and then they got this amazing results. And then, but when you checked the two waves that they were correlating from different places on the Earth, the signal looked different from the two facilities. So this is like, that shouldn't be the case. They should look identical, because
that has nothing to do with each other. So the LIGO experiment essentially has been constructed in Dortmund. It's a German invention, and the mirrors have a mechanism where they are six-fold hinged. So like when you have a balance, it's already difficult to balance your say a stick on your finger, like this, and then think a stick on the stick on a stick on a stick on a stick on your finger to be balanced. This is what LIGO actually is doing, and this is why its measurement precision is so high. Well, the mirrors are massive, and of course they can be calibrated to a millimeter mechanically, literally mechanically.
Okay, well, what about this though? We have the kinetic equation for energy. It's half mass times velocity squared. So if the mass changes because of the kinetic energy, or the kinetic energy changes the mass of the particle, then that means we have to update the mass in the equation. This
naive equation with a half mv squared, this is the root cause of all these discussions. This is classical mechanics. This is not allowed. This is just not allowed. It's not allowed by ice-based means, and it's not allowed by relativistic means. Just people don't get it. They think because they have invented all that mathematical apparatus, they're allowed to do that. But they are not allowed to do that when ice-based has correct basis for all that, because you cannot bend Lego. But, you have a lower end where your math is ending. And when that is true, you must incorporate that lower end in all of your equations. And then happens the following. How much do you need to accelerate until the Lego from level 1 jumps to level 2? That is all about inertia. Think on the following. You have a screen with 8K pixels, okay? And you zoom in with a telescope on your pixels. And then I tell you, make a horizontal line in the center of your screen, and you activate a row of green pixels horizontally and look with a microscope, and every green pixel is correctly switched on your horizontal line. And there's a zero error because all your pixels are mechanically on the TFT screen horizontally aligned by coincidence of the manufacturing. And you say, job done. I activated a horizontal line. Now I tell you, do a 33-degree line. Now, what you need to do is you need to go 3 steps to the right and 1 step up, and 3 steps to the right and 1 step up.
Yeah.
When you look now in your pixels, you see in detail that they are no longer perfectly aligned. They are an approximation. Yeah. When you look from far enough, the green line looks perfectly 33 degrees, but essentially that is a mixture of perfect horizontal lines and perfect 1 pixel vertical lines. Whereas when the pixel vertical is 1 pixel, you cannot even talk of a line because it's sort of an atomic dot. Even in iSpace reasons, there is a line, it's 2 dots, not 1 dot. And that means if you have enough pixel resolution, you can always perceive that you have a 33-degree line, but you never get one. Which means if that is inertia and you want to drive in the 33-degree direction, you would have an inertia resisting until the right pixel comes up to jump up. So you go to the right, one up, not yet. You go to the right, not up yet. You go to the right, now it's okay. And then you jump up one. But what prevented you going up earlier? I mean, from a human perspective, that is the grid which prevented you going up. But this is not the answer because relativity has a continuum, at least mathematically. And there is nothing preventing the thing going up earlier.
Yeah.
But when the inertia would be like on a grid, it would be a mechanical reason in subspace time. Like what we all talk about when Emmanuel is done with the paper, that we have a media. And that media is cell-based, and that cells are hexagonally arranged. In how many dimensions, we don't know until measured, but mathematically assume 6 dimensions in iSpace, but could also be a different number as long as the resulting factors for calculating constants of nature give proper values. Otherwise, it's just speculation. So with that sense said, everything of string theory is just speculations because they speculate something, is an imaginary geometry in their brain, and then say, yeah, and how do you know you're right? Except we don't. There are 10 to the power of 500 configurations, so they know nothing. So there is no string theory. There is a string model. And string model can be bent and played with and mathematically calculated to death on supercomputers, but it tells you nothing. Absolutely nothing. Zero.
Yeah. So, are you saying that there's jumps in inertia? We should perceive jumps in inertia, or
so? This is what I tell you. These jumps are that what inertia is actually keeping up. So there is no continuous inertia which you can increment from your acceleration. You can only accelerate a pixel more or not per distance, and a pixel up or not per distance. And if you discretize this acceleration, you also discretize your speeds, you discretize your mass, you discretize your length. You see the pattern here? And then your inertia becomes something Lego style. And that is interesting because in Lego, you either have that Lego edit or not. But what did the universe do with your accelerate wanting? So a wannabe acceleration is one not yet happening, but the momentum is going in that direction. So there is a pressure to going up on the screen, and not only horizontal, but it is not allowed yet for reasons. And once the reason is able to allow the movement up, it will immediately do, because then it feels better. The particle feels better when it goes up. Would it go more to the right, it would have even more pressure, willingness to go up later.
Yeah. Okay, so, but I mean, with the kinetic, 1/2 times mv squared, that is part of Einstein's equation for, the whole maximum, or the HF equals the
No, it's Newton's, and nobody ever explained the half factor. That's the problem. And now I know where we come from. Sorry for that. So John Louis von Bell explained why the factor 1/2 there is actually in the equation. And with his model, he doesn't need the factor 1/2. It comes naturally. So there's a factor of 2 in quantum mechanics, which is missing, which gives in another equation not 2 pi, but 4 pi. And that is exactly the reason why certain things need to be 720 degrees and all that kind of stuff. This is that multiplicative factor of 2.
Right, but I'm talking about the photoelectric effect, Einstein's equation. He uses the kinetic energy. It's part of the whole equation. So, so he doesn't. He's like, the inventor of this whole relativity thing, if you like, or one of the main people involved. So then, but he's happy to use it. So, you know.
No. Wait. When you say Einstein is the inventor of the photoelectric effect, you should also breathe out and say, yes, what did he show? He showed that something is discrete.
Yes.
Yeah. What has showing something with discrete to do with relativity? Using relativity in your equation is exactly the opposite of showing something is discrete, because you pretend to bend screen. So what my suspicion is, that all of especially common relativity later has been influenced by the mathematical people around Einstein, especially Riemann. And Einstein and Riemann were not even friends, okay, when you put it from a historical perspective.
Sure.
They didn't like each other. But no, Einstein was never good enough in mathematics to do that by himself. So he said, yeah, then calculate it for me, and he calculated. But did he really like the result? Who knows?
But it's necessary, isn't it? It was necessary for the equations to work to use Riemann.
Einstein never got a Nobel for the relativity. That must be stated here. Einstein got a Nobel for being a genius and understanding the photo effect and understanding a lot more of quantum mechanics than all the people of quantum mechanics together, actually.
Yeah.
Well, I don't know about that. I mean, I think the photoelectric effect is like quite a small little zone within quantum mechanics in general, and also is built upon many other great thinkers.
Yeah. In one of the papers I have written with Emery, we show that Einstein falsified himself, like what you were saying about he should have gone with the quantum mechanics. But what I'm saying is that mv square, let me over to it is from the Newton thing. It's actually very simple. It's momentum. It's mv, right? And you integrate that. So mv dv, when you integrate that, you get mv square by 2. Okay, so that's a simple. The other aspect is the why the radiation doesn't occur in the linear range. Why it does occur in the the curved range is because I think that the field, like I said, is consists of gradient and vortex, right? So when it goes straight, it doesn't separate each other. When it goes around, the vortex field separates from the gradient field, and the gradient field goes by itself and emits the light. The gradient field is the radiation, is the light.
Sorry, so could I ask a question? You said differentiating mv squared. It gives
no, mv. Integrating mv. Integrate mv. mv dv.
Right, what does that give you? 2 mv squared would not just be 0?
No.
Or 1?
When you integrate, the m is constant.
Oh, yeah, integrate. Sorry.
So v dv. When you integrate v dv, what do you get? V squared over 2. Right?
Sorry, what did you say there? You integrate the mv, you guess.
Okay, so let me show here. Maybe I can show. Let me put this one on. Hopefully,
you can even type it in your document and delete it later, Rajan, if you like.
Oh yeah. That may be easier. Okay. Hopefully, I can put the integral sign. I'm trying to get. Okay.
Okay. Well, you can even just put I or something. You figure out what you mean. Right. So maybe this is
like here. Let me put it here.
Rajan is right. Just checked it in Mathematica. If you integrate m times v, you get mv squared half. This is correct.
Oh, okay. Yeah. Okay, that's fine. So I was thinking differentiate and mv squared or something, and I was like,
no, not differentiate. Integration.
Right. Okay. So it's interesting. Okay. Go
so
ahead.
V dv. Yeah. When you integrate, you put let's say integral sign. I'll just put a what do you call one of the maybe this one.
Okay.
Maybe let's say this is the integral sign, right?
Yeah.
So mv dv is equal to, I can take m out. So m, because m is constant. In this case, we are assuming m is constant. That's why Einstein. Then we have v dv. This is a classical thing. Thing, m is constant. M doesn't change.
We're not assuming m is constant, though. We're saying that m changes with the.
Yeah, that's relativity. This is classical. This is classical.
This is why I'm confused here.
Yeah, this is classical. This is a Newtonian physics. This is all. This is Newtonian. This is a Newtonian.
But you're saying that when the kinetic energy, that the kinetic energy changes the mass of the particle, but if the mass is constant in the equation of kinetic energy, then
yeah,
it seems like a contradiction.
Don't you see the error while you're talking?
Absolute mass.
Christopher, don't you see your own argument? You say the energy, the mass m is constant. So what in your equation stays is v, and v is a speed. But we never talk about how can you measure a speed. This is what my argument was before.
Well,
you can measure a speed by a distance over time, but you don't even know if that is a valid approach.
If you're saying that the mass is constant, or the mass is constant, but it also changes, then the mass is not constant.
No, I didn't say it changes. What I said, the perception of relativity needs to be correct, or the equation doesn't fit. And when you have only two things, Einstein told the following: when we don't change the time, something is wrong. Okay? Yeah. That was the enormous thought where he was showing in super simple special relativity that when you have a speed and you near yourself the speed of light and you don't compensate with theory of relativity, everything is very wrong. And people have not seen that before because the masses needed to be so high and the speeds needed to be so high. And then the Merkur-perihelion was used as a first measurement to falsify or agree with him. And that expedition at that time was also very well planned, but actually they didn't even measure the right thing there. So it could have been falsified also by their measurements at the time, and it was a historical lucky accident for him that the photo plate showed what they showed. So they showed in favor of Einstein.
Even from a computer programmer perspective, like yourself. So if we were to change, like we have a list, and if we change the list while we're operating over the list, that's going to cause problems. That's what I see in this.
No, wait. What I'm saying is when you have n variables and multiply them and things increase, then either one of the variables have increased or the other variable have increased by half each, for example. You cannot know what happened before you look in detail on what you multiplied.
Yeah, but then if you go back to the equation though, then to get like volts, you still use the same mass of the electron.
As I said, this integration from Rajan is exact because it's multiplicative. But the equation is a plus EC squared. This is not multiplicative. And here all the trouble starts because when you make a plus sign, you're not allowed to add apples and bananas. You need to only add the exact same thing on the left side of the plus and on the right side on the plus. And if accelerated mass is not exactly the same than rest mass, here you go, mistake. And big mistake, please, because that is just not allowed to add apple and bananas. And all equations, which shows you that you cannot add speeds. You can only add squares of speeds, and you cannot add mass. You can only add squares of mass. Does that remind you on something? That's why all these equations don't hold under the root. Under the root, they become approximations because they are just not allowed to be made this way. In square form, they are correct. So the relativity on the left side says E squared is, which is correct. But this does not mean you could calculate the energy not squared. And now think what actually happened in the equation when you say E squared. The first equation, the mc squared, is a multiplicative one. And that is the exact one because it involves the rest mass. What the equation actually should write is E is m0 times c squared in brackets. Okay? And that is undisputed the correct one. M0 is for example, take the electron, then you have the electron rest mass, which I calculate in I-space theory. I don't calculate relativistic masses. And that is the thing why.
Yeah, but I mean,
which I stated, the gluons might be just electrons. Would we know the relativistic factor and the real speed with them?
Okay, but if I'm saying, and if Fermilab is saying that there is no change in mass because of speed, then rest mass is irrelevant. Like rest mass is just the mass.
Yeah, but how can rest mass be irrelevant when you need to compensate with magnetic energy for every revolution? It is very relevant. Otherwise, you wouldn't need to increase.
But in terms of, well, I think you're moving goalposts there to something else. But in terms of what we're speaking about, rest mass, and then relativistic mass is when is when the thing is moving at speed, so it gains mass. Rajan's saying it's to do with kinetic energy. That's why it gains mass. But we see that that can't be the case because the kinetic energy equation is 1/2 times.
When you accelerate the particle for over, say, a month, they don't do that, but assume it as a thought experiment. You put all the energy of a single experiment in CERN and put the acceleration of a single, let's say, not a proton. Let's just take the lab. This is easier. You go to the lab in Hamburg, and the lab would accelerate electrons. It could also accelerate positrons at the same time in the reverse direction. And when you accelerate them, they can become as heavy as protons and even heavier. So the longer you accelerate them, as long as you have enough magnetic energy to keep them on the curve, they become heavier.
Okay, but if Fermilab finds a different result, so we can't use, one seems to contradict the other. So, and then when you're talking about,
I don't buy this Fermilab result that things don't get heavier when accelerated in a curve. If the Fermilab is doing a linear acceleration, we can talk about that. That might be an effect we have not seen.
Well, yeah, that's a good question. Fermilab is not a linear.
Fermilab has a linear accelerator, but they also have curved ones. I don't know which one you mentioned now here, but
I'm pretty sure I'd say it's the circular one, but maybe they've done it on both, so I couldn't say. But the other issue is you're talking about doing it for a month. I mean, earlier you were saying.
Why did I say that? It becomes heavier and heavier and heavier as long as you have the energy put in. We ignore the Bremsstrahlung for the moment, the energy going away in form of light because of the curve. And the thing has then 0.9999999999999995673 times the speed of light, but not the speed of light, because it will never reach speed of light. Never.
I don't think it will get, like, if you run it for a month at the same speed, I don't think it's going to
get... How heavy does it go? So when the equation of Einstein...
Wait a second. Like, it's not going to get heavier and heavier. Once it reaches, like, 99.9 the speed of light, it's going to get to its mass. This is the theory.
I show you that in eye-space theory that you get what I'm... Can I share my screen, please?
Yeah.
Oh yeah. Let me take off this one.
But in terms of relativity, that's just not the case. I mean, it gets to a certain weight and it stays at that weight. That's what I've seen in the equation.
No, it does not.
Are you sure?
How would it?
I could.
In theory of relativity, you can accelerate infinitely long. That is the main core of the idea of relativity.
I don't even believe that it does gain mass. So I agree with you.
If that is correct or not, we don't need to argue here. We're not on the different side of the boat. Don't get me wrong. I just want to make a point which is overlooked. I believe this is overlooked.
Yeah, that's fair. I'm always on board with these investigations.
I can see things in eye space which most people cannot see because they don't look that way. And they are rather super simple things. And I've done all that relativity calculations and they made absolutely no sense in eye space. They made so much no sense that I said they are nonsensical.
That's interesting. You should go into that sometime, Christian. Break that down. Even now, if you want to, I don't mind.
I want to.
Oh, sorry. I haven't. Your screen hasn't. Oh, maybe that is.
No, I haven't clicked present yet. How do I know? I have no folio. No. My computer. Here it is. Okay. Don't show me the tips. I don't want to download something here. I always get trapped by this UI. Present. Not. Is it video.time? No. Share screen. Here it is.
There you go.
Share my.
I'll be back.
Everything. Allow security. Now I'm sharing. Okay, and if you allow me to share, my screen will be visible in a moment. I remove the window, and you should see a plain Mathematica window here.
Yeah, I see that.
It is calculating in the background, and I hope it has done it. That I have my I now clicked the wrong Mathematica version. I'm sorry for that. I have two Mathematicas, as you can see here. I just neither wanted nor allowed to start two in parallel, not even license-wise. So I have to wait until that is over and close it again. And I don't close the wrong one, because that will give a mess out of memory and other things. So this is the right Mathematica which I want, I think. Yeah, this is Mathematica 12.1. We want that. And that needs to be closed. Yeah, that in one we close. I'm sorry for the confusion, but this is important now. What I did while we were running in the background, I just run this my simple iSpace base equation stuff, not the complete one, because I came unprepared into the meeting. So I have here, for example, now the electron mass and the electron charge. And I make it bigger for everyone to see here. Let's even go to 200 or something like that. That should be well visible. Or it's 150. Yeah. Can you read it?
Yeah, it's okay.
Thank you.
Yeah.
So what I wanted to show you, when you have the electron mass, which is this term here without iSpace basetime and stuff, it's hard to understand how numbers could bend, right? But if you look at it from a purely numerical part, everyone with a sane mind would say, yeah, why not change so many things after the comma? You have no comma. This is the first thing what I wanted to show you. This exponent and this number is just in your brain. What you have is this. This is exact. And you can compensate it by this 7 times 40.
Is it the human factor?
No, this is the
Walton ratio?
The iSpace basetime human artifact factor, which is just due to the definition of SI. This is not in any way wrong. It's just by the definition of SI. And when I compensate that to the power of 3, the equation becomes simpler. See? So once again, to show you, this is IME in SI, because otherwise you wouldn't get the correct numerical value. Sorry. Here you go. Yeah. And when I compensate with the iSpace basetime factor, only the 1/6961 stays. And you get a very, very small number here, which is still your electron mass as electron rest mass. And the only integers you have after that, which you can play with or make them longer or bend them in a way when we talk about increasing of mass by movement. Movement is a continuous thing in relativity, because you can arbitrarily slow accelerate. And I mean really continuum arbitrary in that sense. And when I factor that, what can accelerate here? The numbers which are staying here is the 483 and the 23. And when you multiply that, you see this is just the iSpace electron mass. So this is not bendable. This is a constant as can be. Actually times 10. So this is the electron mass, as I proved in the other paper. So what stays in the electron is geometry. Golden ratio could bend in theory. P to the power of 3 could bend here. But the 6961 is the quantum of time squared. And there is nothing else in the equation. So what can bend here? Surely not the time, surely not the mass or the rest mass. So the only thing bendable.
4, 6, and 2.
So this might bend here, okay? Let's call this the bendable factor. Bendable factor, because I cannot exclude that, that this is a continuum factor.
Okay.
And we would get a bendable factor numerically, that we have a number of a factor about 50. So when we bend that factor, we could stretch it to 1, or we could expand it to something else. And now let's do a little bit relativity. Relativity is the root of 1 plus, not times, c squared over your speed squared, right? Let's call it I speed here, that's the variable, and we have not defined it yet, but this is the equation of relativity when you look at it. Now, when I define I speed to 1, this is meaningless because I'm not set in which reference system I am. So I could define IC to the speed of light, then it would be the speed of a photon. I speed of photon would be IC, and when I then calculate here just simply I speed of photon, then you get 1 plus 297,92458 under the root, and when you make that numerically, sorry, did I square it? I have to square it, of course, that's why it's wrong. You get the root of 2. Why do we get the root of 2? Now I'm confused.
Yeah, seems to be the output.
The factor is root of 1 plus speed of light squared to the...
Right. Yeah, that would be 1 plus 1, so the root of 2. Right?
Yeah, but the factor should for the speed of light be infinity. I'm doing something wrong here. Ah, yeah, minus, of course. And it's 0, and this is not allowed, yeah?
I thought you said it was plus earlier. Why is it minus?
Yeah, sorry. It's just, we can calculate it.
1 minus v square over c square.
So.
Oh yeah, okay, you're right.
So this is not allowed, but this is what the photon is doing, even if it is so the photon is doing already something which is by the Einstein equation not allowed. This is a simple argument, isn't it?
But is that because the photon has no mass?
Good argument. No mass means 0, but nothing has 0 mass. This is the main problem. Why do you assume it has no rest mass? So a photon, when you have a photon, and we call it I mass of photon, is I rest mass of photon plus I dynamic mass of photon.
You're saying the dynamic mass is 0.
Initially, when the photon would be at rest, the dynamic mass of photon would be 0. So we start with that, and I show you later where the mistake is. The rest mass of the photon is also 0 per definition. This is not a mistake. This is okay, yeah, per definition.
Yeah.
So what we get here is a mass of 0, and now tell me the mistake. I can see the mistake immediately because I have iSpace eyes on. Can you also see the mistake?
Dynamic mass.
The dynamic mass of a photon can never be 0 because you have ZPA, 0-point fluctuations. Nothing ever is at rest. It would be 0 if it would be at rest, but it has a microscopically small mass of the ZPE already. And even if I make it as small as this, because this is just an arbitrary scaling here, just to show you the effect, then I gave it as a 1 over 10 to the power of minus 27 minimum mass of its ZPE energy, but not 0.
Well, what does it mean, the rest mass? Like, if the
anything in the universe which is under existence and consists of particles has a movement, because nothing is ever at rest. Ask your local equation for Boltzmann constant, okay?
Okay, but what's the rest mass? If nothing can be at rest, then does it mean anything?
No. When the photon is presumed to have a rest mass of 0, and the photon is emitted in form of energy, the energy of the photon is the same in the strong equivalence principle than a real mass. Either Einstein holds or Einstein does not hold, okay? And if Einstein holds, the mass of the 0-point energy of the Zitterbewegung is not 0. So it will have a dynamic mass which is not 0 initially.
But isn't that what we say from the point of view of like Planck's, the energy?
No, this is a way bigger energy. This ZPE is extremely small. I don't have the numbers now right here. We have a physics book upstairs which showed me that.
But isn't that the mass of the mass of the photon is based on Planck's constant?
Look, with the Boltzmann constant, you can calculate the energy in form of a temperature. This is equivalent, okay? And when you say a mass, you can have minus infinity energy, plus infinity energy. That doesn't give you a real thing. But when you calculate with KB, with the Boltzmann constant, you immediately see that there is a lowest temperature, and that is 0 Kelvin.
Okay.
And you never reach 0 Kelvin. You never.
Yeah.
Okay? You might reach 0 dot something Kelvin like this, but not 0. And it doesn't matter if I say the dynamic mass of the photon is not 0 because you never reach 0 Kelvin, or this argument is moot. It is not absolute.
It's because the electron spin remains, right? So
we don't know. It is anything in the universe itself has movement, and I think it is the background. So the ether as a background is that what spins, and the Zitterbewegung of that, what Emmanuel has written in his last paper, which gives the resonance to get superluminal speeds as a surface wave, is that what we see as a rest energy there. This is extremely small, but not 0. And as this affects every movement, it is also affecting theory of relativity. And if it affects theory of relativity, then this equation is not precise, because then this equation means you need to do here I ski squared of photon plus this dynamic mass of photon. And suddenly this equation is not 0 anymore. And if it is not 0 anymore, I can calculate it. Because Mathematica has an arbitrary number. Now I need just the units. Why does it do that? It should combine these numbers. Because of the 1 is not exact. So of course I need to tell Mathematica that this is an exact value. And
so are you attempting to
also an exact value, then this is also an exact value, and then it will be able to do that. No. What the hell? Now you see me really a bit confused. This simple equation should... this is the units I'm missing. Sorry. I need to give that thing a unit, of course. My fault. So we need here, of course, a meter per second unit. Mathematica is, if you do the wrong units, you get your consequences immediately. Okay? I add meters per second and meters per second, not apple and bananas. Yeah, so that is fair enough to see. Maybe I should have done this way. And then we get a result. See, we get a result. This is what I wanted to show. So we have the 2.5288 to the power of minus 18 factor here. So that is now the smallest thing you can think of. I can make it smaller by adding a few zeros here, but rarely less. Yeah. And this effect is as small as it is in I space not allowed. This violates principle of equivalence. Of course, physicists don't see that because it's so small, then they leave it away and say, yeah, this is just a third order term or fourth order term. No, the principle of equivalence tells you you have 0 error. It's equivalent rest mass and non-rest mass. And rest mass I can define here precise, ultra precise, not negotiable, it's an integer. And when you have this factor here, this bendable factor, and you multiply the bendable factor with that, you get quite a high thing suddenly, yeah, minus 16. That comes into a range which could be even measurable. And suddenly you cannot negotiate it anymore. So
is the dynamic mass of the photon?
That is a perceived non-exact mass of the photon. The problem is the rest mass of the photon in all equations, in all books of the world, is perceived as 0 because it says so. What I tell you is that is wrong perception, because you're not allowed to leave that 0-point Zitterbewegung away, and when you say anything, whatever it is influenced by Zitterbewegung, and I did a really, really slow energy or mass factor here, but you see what the relativity equation is doing. And when you do the reverse, and that is the evil thing. Now look at the reverse. What we could do is we do that to the 999999999999999, and then something random. So like accelerator would have run for a month, yeah? Then you come here. When we do it like this, then we reach this factor, nearly the speed of light, but not yet the speed of light. And all I want to show you is that with the precision of Mathematica, you're suddenly able to see that.
So what is happening?
Do you see the relativistic factor here?
Yeah.
This is 0.04. This is massive.
Yeah. So what is happening is that the photon at rest suddenly accelerates. It's like a Dirac function because it's at 0 velocity, and it attains the velocity of the speed of light in a space. I don't know what space it takes for it to accelerate to that level. It has to be the Planck space or something.
Yeah, but Rajan, you cannot accelerate anything to speed of light in 0 seconds. In your math, you can do that. But would you please agree that in the real world, this is not possible?
Yeah, that's what I'm saying. So it has to travel some distance. The photon has to travel when it is rest and is getting emitted. It has to travel a little bit distance for it to accelerate from 0 to the speed of light. What is the distance? You know, there has to be a very small distance.
High-space theory has an answer to that, and that is if the subspace rotates already with speed of light, then something gets emitted by losing a couple of pixels of the edge of the rotating LEGO entity, and later the energy must need to be recovered from vacuum, because that vacuum would otherwise have a hole, and the hole must repair itself energetically. Yeah? And there's always enough photons or 0-point photons turn around. They get energy-wise not an inconsistent value, because energy cannot be created or destroyed. Energy can just be converted. Hopefully, we agree on that. So,
well, then isn't there an issue there though? I suppose, well, maybe it's a flippant thing, but like you have this particle with a certain amount of energy, which is its mass, but then as it accelerates, its mass goes up. So energy is being created in that sense.
No, it's not. Why would energy be created? Something accelerated it, and that acceleration energy is transformed into the speed of the increased speed of that particle. There is nothing created.
But then wouldn't it slow down if there was a balance? It would have to.
Yeah, it does slow down because the speed increase of anything in the accelerator is slower and slower and slower, because with more of this equation, which I showed you, it gets heavier and heavier and heavier.
But the speed is still going up, or else the mass wouldn't go up.
The speed is slowly approaching the speed of light and is not going up anymore, because the speed of light cannot be super. It gets heavier and heavier and heavier, because you have this multiplication of speed v and mass m. And if you have only two factors, you need to increase m, or you have to disbalance your equation.
It doesn't get heavier and heavier. It gets heavier to a point, and then but it's relative to its speed. It's like,
no, not relative to its speed. It gets absolutely heavier. And you see that when when you do an accelerator experiment, this is quite easy to switch your magnets off. Yeah. Yeah. And as the curve is so long, it's 40 kilometers in the ring, when you know your particle is actually not one particle, it's a group of particles moving there, let's say 1,000 atoms or something in an accelerated group of protons, then you know exactly how long they need from one end of the curve to the other end of the curve, so to half of the ring. So you know when these particles with nearly the speed of light group will reach this 20-kilometer ring times 2πr or something. And if you switch electrically by a computer, coordinated that off, then they leave the acceleration tube to the collision room where the target wants to wait. And when you hit the target, you get a calorimeter there typically, and it gets warm where the particle group hits the plate, the metal plate or whatever it is there, where lead, and it gets measured in the temperature increase in principle. So millions of particles hit their average, not a single you will not notice. And then the average heat increase in the target tells you how many particles hit the target with what mass. Because if you have a cannon with a cannonball and you shoot it with only 1 meters per second because you have a lousy cannon, it will not make much damage on the ship on the opposite side, right? So 1 meters per second of the 10 kilo or 1 kilo cannonball doesn't destroy a ship.
This is but kinetic energy, I guess.
A 10 gram bullet, which is accelerated to half the speed of light, evaporates the ship when it hits. In a thought experiment, what do you mean? It's a normal bullet, like a bullet from a pistol, but half the speed of light hitting that a ship it detonates
temperature. The temperature, the Boltzmann, right? Boltzmann equation.
Because it has such a high mass.
That doesn't really prove like anything though, because you've got the velocity term. The higher that goes, the more kinetic energy you have, the more
v squared. Square term, yeah, it's a v squared term.
Sure, yeah, but I mean, you know, it's still going to go. Yes, so it's going to be even bigger. Like each time it goes up, it's squared. So,
Christopher, let me calibrate for a second. Where do we actually disagree? I have not the feeling that we disagree with each other, so we should not discuss around things which
no.
Can we quickly calibrate where we're on the same side and where you think things are different?
Sorry. Yeah, well, no, I think I'm saying that there's two interpretations. One is that the mass increases. The other is that time slows down, and these are mutually exclusive. It has to be either one or the other. So,
or it can be a combination of half the mass increase. So it's a strange world, but it is also possible, right?
That's fair enough. But I don't think there's a between the two camps. There isn't really a compromise between those two.
Yeah, but I showed you just if your world is discrete and you have a slight increase, this slight increase will not be bendable. So if it is not bendable, it's not compatible to relativity. And if it is just a little bit not compatible on the 29th digit after the comma, it doesn't matter for the argument, because if anything after the comma is not compatible to the rest mass, then you have not the principle of equivalence halted, then you have it violated after the 29th comma, after the digit after the comma, but nevertheless, if the equivalence principle don't hold, game over.
Yeah, well, I'm not disputing the equivalence principle, I don't think so.
Anyone who is accelerating in a bendable continuum is doing that without implying it is irrelevant. And I'm just reminding you to rethink that it is relevant. You cannot do that.
Well, yeah, no, but I'm not. I don't think I'm saying that, but well, I'm not. But yeah. So I think you were showing something there. I would have thought that the idea that even over time that the mass increases is incorrect. I could be wrong about that, but I thought I understood that.
The time cannot be slower or faster in my equation, because if you put I-space input values into it, these I-space input values are integers and will not change. They will just not change.
But the other issue you have to contend with,
so this factor 50, this geometry, golden ratio times power p to the power of 3, that could change.
Well, I mean, I'm sure you have considered this, but like if you're on the one hand, you're showing, I suppose what you're showing, I would say disproves the position of relativity anyway. But then you were also saying that the rest of I-space also seems to disprove a lot.
What I'm saying is, in iSpace, you see why the theory of relativity is incompatible with quantum mechanics, because the theory of iSpace is fully compatible with quantum mechanics. Otherwise, I'm not able to calculate conserved nature. And the relativity has the same problem with the quantum mechanics than it has with iSpace. It doesn't fit in a discrete model. Hence, this is the reason I invented these 6 additional subdimensions. Then it is compatible.
Okay, I understand. Yeah.
And now think of it. If it is compatible with 6 subdimensions, which are strictly Lego, then your movements are not of that Lego pieces. Lego pieces don't move in a continuum because they don't even exist in a continuum. What does exist is Lego pieces which have weight in subspaces. And if you move objects in space-time, you move subspaces containing these masses in space-time. In other words, you move the box and not the particle. So when you have a box, and think of a simple water experiment, any children has done that. You make a 10-liter cleaning pot with water, and you start rotating that pot. Then it gets inertia, and the inertia rotation of the pot is run together with the water. Then you suddenly stop the pot, and the water inside the pot is continuing to rotate inside the pot as long as friction of the molecules lasts. Quite long, actually. And why is that? Because you have something like inertia, the unwillingness to stop movement if no force is exerted on you.
Yeah. Right.
This is not how inertia is defined, but how you can see it.
Yeah, sure.
Yeah.
So what do the water molecules do when they rotate in the pot? Why didn't they recognize that the pot has stopped? And the answer is that the molecules in the inside, which are not directly have contact to the wall, have no idea that the wall has stopped. Why would they? They have not even contact with them.
Yeah.
So there needs to be an information once again from the border of the pot to every molecule in the system that the pot has stopped, and that is happening molecule by molecule. So the molecules inform each other about the pot stop, not in a direct way, not in an informatical 0-1 way, but every molecule tells a little bit, hey, can we stop? The border has stopped. Can we stop? The border has stopped. And when that information has reached all particles, then the water is calm again in the pot before we started rotation of it on the plate.
I suppose, but you need mass for inertia though as well. So it could be.
So would the water have no rest mass? It could have stopped immediately. Why not? Would violate no law.
No, I think the energy transfer, right? The energy is now transferred from rotating thing into the water. Because
yeah, that is a good point, Rajan. This is indeed what, when you rotate the whole pot, including the water, you gave mass inertia to not just the pot, but every water molecule in the pot.
Yeah.
But so the water already had inertia, though, even when it was at rest. Isn't that the whole point of inertia?
Maybe then inertia is the wrong word. So this energy, in your equation, what is behind your plus sign? This P plus C squared. This is what you gave to every of the molecules when you rotate the pot.
Momentum.
The energy.
Momentum, yeah. Momentum and inertia is, of course, not the same. But momentum is the desire to move forward in a grid in X, Y, Z direction. 3 dimensions.
Right.
Yeah.
So, but what is desire of movement? From a programming algorithm, as I showed you, the Bresenham algorithm says 2 to the right, 1 up, 2 to the right, 1 up. That is also momentum, just a digital one. But if you cannot reach the pixel positions, then you have the desire to go there, and the reality check says, sorry, like we go in a door. And we said, I want to leave the house. I cannot find the exit. It's your problem. You are hidden in the house. You are caught in the house until you are clever enough to find the door or smash a window. So your desire to move somewhere is meaningless if you have not the physical ability, like in the quantum mechanical sense, to actually have a path there. If you have a path there, you can suddenly leave the house.
Okay, but then what if it's, so you're saying that over time the mass increases as it's
yeah.
approaching?
So one of the things about the mass,
and
the
then
mass increase.
the mass is still increasing over time, even though it's at a constant speed, let's say.
Yeah, but not the rest mass. The relativists say that the rest mass is the same as in the plus, with the PC screen, and that would mean in one single equation added up, the mass increased. But what I'm saying is the rest mass did not increase, and something gave the appearance of a mass. Otherwise, the relativity wouldn't work. But what can appear like a mass but be not a mass?
Well, then the other question I have is, so let's say it's traveling, and then there's the inertial thing where it's gaining resistance. Does that mean that its inertia goes up or not? I mean,
yeah, of course, with increased mass, your inertia goes up. Yes, of course. Exactly, that happens.
As it's traveling like through time, would those inertial jumps that you're talking about compound, or do they always reset to zero each time?
Think on torque. It's easier to visualize. If you have a normal combustion engine, or if you have a carousel for children, it doesn't matter. You have a 2-meter diameter carousel for children. No one is sitting on the carousel. The carousel has a rest mass of, say, 1,000 kilograms. Yeah, so steel carousel. And with your hand, you turn the carousel to 1 meter per second angular velocity. Doesn't sound much, but when you sit on that as a child, you get whirled around your head once in about 3 seconds. And if I accelerate you faster, you quickly fell off because you get even unconscious by that simple angular speed already.
Yeah.
Now, when you try to stop the carousel to save your child from this acceleration, your hands will burn because you need to have friction with your hands on the metals of the wheel, which were used for acceleration to de-accelerate the carousel. This is one thing. But have you ever tried to de-accelerate something on the axis? So when you take your hands on the axis of the carousel and try to break it there, you get to the hospital after that because your hands will be for sure end up in a blood mess. They will melt.
Right. Yeah.
So many body problem, right? It's like a many body problem.
So you have no way of stopping the carousel with the force of your hands when you're not fitting it on the outside of the carousel, but when you try to fit it on the center. So any rotational angular momentum is not stoppable. And when you have, this is also how I believe where rest mass comes from. When you have something actually going with the speed of light and is light, you cannot stop it because light is either exactly c or not existing. There is no slow light because a slow light in a medium has still the speed of light, but the medium makes a deviation, so the path is longer for the light. There are experiments that you can bring light even to halt and near stop it into a crystal. It has a speed of few centimeters per second, or sometimes even centimeters per hour or something. So extremely slow light is just experimentally possible.
Yeah, I agree.
So that question.
So, what does the medium tell the light? It makes an ultra long path for the light. It doesn't stop the light as such. As a photon is not moving slowly to the crystal. The photon has never a different speed than c.
Yeah. Yeah.
See, the question is, suppose particles moving and its mass is increasing. So the inertia is going to increase, right? Inertia keeps increasing. So there will be a friction. Because of the large inertia, there will be a friction. That's what Wenzhong was saying about vacuum friction. So when it is when it increases the mass to about certain level inertia, it's going to create friction, right?
Well, maybe. I mean,
even though it's supposed to be, that's vacuum friction. So the thing is that anything, if it goes above certain mass, the friction factor becomes larger. So it's going to create heat, the friction. So
I think you can see it that way, Rajan, because when you increase the mass relativistic, you get to some relativistic factor which gets you close to C, but you will never reach C. and then your mass increases and increases and increases. Purely mathematical, because this is the only variable is m which you can increase if you're not allowed to increase c anymore.
So
Just
going back to our simple equation here, mv dv. Suppose the Einstein thing, the m is not constant, so I had to put it in the integration factor, the m also, and that m naught over 1 minus b square over c square, square root of that. And then when I simplify it, I can take the m naught out, the rest mass, and everything inside. You get 1 over, then I simplify the v and everything. Then I get, I did mentally, but I think this is correct. So 1 over v square minus 1 over c square to the power of negative square root, negative, 1 over square root, negative 1/2. Do you see that complex term here? This is what you have to integrate. So it's not v square over 2 anymore. You can see it won't be v square over 2.
Obviously, you get the -1, otherwise it wouldn't work like relativistic equation.
Yeah. So now the v changes. So it's not v. So, to answer Christian's, Christopher's question also.
Yeah.
Now, when you go from the classical to the relativistic, it's no longer mv square over 2. See, this term is not longer, is not m naught v square over 2.
Right, that's a different equation though, isn't it? To the one that appears in the photoelectric effect. But so you kind of change the terms around a lot. So that work in that domain, I guess.
So I'll briefly continue.
I think you're going to get some different answers.
If I may, I can continue this, right? Little bit more.
Yeah,
so next time, I don't know whether we'll have enough time to code today, but we will continue. I just want to point out the abnormal medium where the group velocity can be faster. And then I go to last time what we were talking about, the QN bit. So I convert this one into, into our information, IT type of thing, that I make into. See, what I can do here is I can use a determinant, divide by the determinant, and normalize it, and make it to go to 1. So eventually I can get to 1, 0, 1. Okay, not 1 and not 0 that we discussed last time, and on off. Then I use something called mathematical constraint. What I said was, in order that we can calculate, I say I equate the bar 1 equal to bar 1 equal to 1/2, and then not equal to 0 equal to negative 1/2, off equal to 0, on equal to 1. I get this equation. So now I can compute, right? I can compute QL and QG 1/2, and then I change the bar 1 equal to 1/4, negative 1/4. So now the value of QL is 0, but the QG becomes 1/4, and so on and so forth. I can keep doing that. Then if I say I switch this around 1 and 0, so I have permutation here, and then 1, 0, then QL becomes 1/4. Okay, so I can map the whole thing, right?
Well, wait a second. How do you normalize to not 1 or not 0? What is the mechanism to normalize to those values? Is that possible?
Not 1, not 0 is that the 4 factor, the 4 vector, right?
Yeah.
4 vector says is that you can have 0, 1, but also it may not be 1. Not equal to 1 is, it may not be 1. It may not be completely on. We discussed that. It may be completely on, or not completely off.
Definitely not 1. Seems like it's saying it's definitely not 1.
Definitely, yeah, because we already considered 1 here.
Right. So
the 4 vector, everything should be different. Everything should be different.
You properly
so
here, Rajan?
0 and 1.
No? But then you have 1 could be 0, which means that it would be the same as the term on top.
Yeah, that's a trivial solution. That not equal to 0 equal to 1 will be a trivial solution. V1 non-trivial, right?
But Rajan, you're calculating probabilities here, right? Because when you say you normalize the equation from anything in a matrix, you can of course change the matrix in a way that only the values between 0 and 1 remain from that whatever values you started with. That is exactly. Just this is allowed. This is no problem.
It's a probabilistic.
It's a scaling thing.
The problem is saying not 0, you know, because that's like a new number. It's like not between 0 and 1. It's like a different number. It's almost like a.
But it will be closer to 0. See, what not equal to 0 means it will be closer to 0. Not equal to 1 maybe closer to 1. So that's what implies. But I can change it. I can give a value here, not equal to 1.5. So I get that some values here. I can keep changing. What I mean is that this can vary anywhere from 0 to 1, but we will see that it has to be quantized. It's not continuous. That's one of the big things. So what I'm saying from physics, okay, the phase angle, for example, you can the phase angle or Q factor that Gerd is saying that the phase angle is not continuous. It's quantized. So you don't have like your angle of 24.1. You don't have 24.00001. It's not continuous. It's actually quantized, which means if the phase angle 24.1, next angle may be 24.8 or something, because you, like Christina was saying, there's a definite space between two particles, even though they may be extremely small, but that prevents it from the angle being continuous. So you have to consider the space between the two, like there are two atoms, two particles. They cannot go into each other. So the next particle has to occupy a different space, like he says Legos.
Well,
has to occupy a different space.
Bosons, though, is it? I mean, you can have a boson traveling one way and a boson traveling the other way, and they'll go right through.
Yeah, but once it occupies one space, another boson cannot go in there.
I think
that space is occupied.
I think you're thinking of fermions, your Pauli exclusion principle, and those two cannot occupy
no.
energy.
Any particle, even boson, suppose it occupies space x1, y1, right? Exact space. Okay.
The Pauli exclusion principle only holds on the electron shell, Christopher. Though the Pauli exclusion principle for a whole atom is moot. I mean, this does not exist.
Yeah. Okay, but I think there is they do talk about how if you were to switch to any two, well, maybe that's slightly different.
You cannot put two particles of the same state, phase, and all. So if you would know by measurement and physics theory all its states, then two particles with the exact same state cannot occupy same space if they are fermions. That's correct.
Yeah, if they're fermions, but we're talking about bosons can. That's the difference between fermions and bosons. They can go right through each other.
Like but what you say bosons? Why do you say plural? There is only one boson, and that is the photon.
Fermion as well, according to Feynman.
So. No. When people always say fermions and bosons, so show me the second boson. Which bosons do we know? Light and more light, or what is that?
Well, yeah, exactly. You can have two different wavelengths of light, and then they
but these are still bosons. This is so we have one type of boson. So I think the whole distinction in these groups is nonsense.
You can look at the standard model and find other bosons in there if you accept the standard model, but you know, in general,
you cannot find more bosons. Any boson is light.
Two different fermions. If I have two photons, then you have two different bosons, and those two bosons can pass through each other, so they can exist in the same space.
Light can pass through each other. Exactly. It doesn't see each other. You can have two lasers cross and nothing happens.
Yeah. So
but exactly. You cannot have two electron beams cross and nothing happens because they will disperse. It will happen because they see each other.
That's what I'm saying. So there's an exclusion principle in the fermions, but not in the bosons.
Yeah, but have you thought about the geometrical reason why that is? I mean, when light is moving outside of that box in 3 dimensions. And the boxes itself are 6-dimensional, then the boxes see each other boxes, whatever is in there from a mass point of view. So boxes see other boxes. That is called fermions. And now you know why boxes cannot be on the same space, because a subspace is already occupying that x, y, z coordinate in 3 dimensions. And another box cannot go there. Whereas light is not doing that, or at least some wave types might not do that, like gravity waves. We don't know that. So the speed of gravitons, would they be particles like photons, can also not exceed the speed of light. That is proven by experiment, also by the LIGO experiments, as we have seen that the light of the stars, when they explode, come at a definite time with the ratio of the speed of light c with the effect seen in LIGO. So that is
we do have a lot of evidence that the speed of gravity is instantaneous, or else
yes, but only in Newtonian form. So it's even that simple that Newtonian equations wouldn't work if you wouldn't allow superluminous instantaneous action.
Oh yeah, but the universe as it is wouldn't work, because
yeah, I heard that and read that, but it makes less sense in the theory of relativity, right? Because in the theory of relativity, nothing must exceed the speed of light, not even gravity, and hence the speed of light for gravity would make wrong predictions in relativistic equations, and hence they have to bend that relativistic factors that everything is correct.
The two things are different, though. Like if you have the sun and the Earth, if there was if the gravitons, let's say, or whatever, the force of gravity took time to get to the Earth, then it would there'd be a delay, but there is no delay in the system, because if there was a delay, then everything would sort of fall out.
Yeah, in the three body problem, the planetary orbits wouldn't be stable. That's simple. Not even in Newtonian form. It doesn't need to be relativistic corrected. The Newtonian form of the bodies, and it is in good approximation, is good enough to calculate Newtonian equations for this solar system, with all due respect. Yeah. And that would not work if you don't assume gravity is instant. Yes. I've not read the Principia Mathematica from Newton, but would you have read it? There is nothing written about the speed of gravity there implied or explained. No, he has not told us what he has thought about that.
It's something that is accepted, from the point of view of how the universe works, and does seem to go against the other.
Yeah. So the main reason is, why wouldn't we, or any theory of relativity supporter and quantum mechanics supporter, which are most physicists on the planet probably, why would they object instant action at a distance when they not object instant information exchange at a distance at the same time? Have you ever thought about that? EPR effects are instant information exchange at a distance, and they completely accept that because it's experimentally proven, no problem. It's a big problem because it's actually superluminal if you put it the other way around. But they say, no, it's not superluminal. We just define it in the equation as instant action at a distance. I say, okay, then let's assume gravity has a higher speed than c. Then they come with the argument, no, at no way, nothing is faster than c. Do you see how they are locked in their own thoughts?
Yeah, of course, yeah.
When it feeds them, they put their favor argument out that nothing is faster than c. If it is informational, suddenly it is allowed that something is faster than c.
Yeah.
But one could also argue that they don't know what they talk about.
I agree. I find that argument to be the most convincing.
The speed of gravity thing is a serious thing experimentally to be verified, and I'm not sure why that is so difficult. We had 100 years now with spacecraft creations, more or less. Yeah. Why can we create satellites who solve that question experimentally?
Actually, I have in
physicists who have solved it. I've forgotten his name.
I have given in one of the science forums, I have shown how the gravity could be measured by satellite. I can pull up one of the thing. I have shown that the satellite moves. You have to produce like neutron or something to see whether they are the neutrons that are gravitationally attracted, and then suddenly change. I have shown a design, means I have explained how that could suddenly, the satellite suddenly moves and you can measure it. So when you measure it, actually you can measure even speeds, very fast speeds, c to the power 4 or c to the power 8 we can measure. The satellite has move, because when it moves like that, the equivalent speed is c to the power 4. I have to pull up that article, and so you can measure it actually by using two satellites.
I'm not sure what that has to do with the. I suppose the satellite is being pulled by gravity, is it? So.
No. Two particles in the satellite. Two particles.
Oh,
so
yeah.
The interaction between two particles. There is one particle in one satellite, another particle in another satellite, and the interaction between them.
Well, it's entangled, are they?
Gravitational interaction, like a neutron, or something.
That seems very difficult to measure.
Yeah, I have
what I have heard is that they are planning a satellite where a 1 kilogram mass inside the satellite is floating inside the satellite, making a mirror on its edge reflecting for a laser beam to measure the distance between the cubes of the satellites, but floating free inside the satellite so they are not exposed to any radiation or other gravitational effects except the hull mass of the satellite itself.
Right, but they would still feel the gravitation of the Earth, wouldn't they?
Yes, they will feel gravitation of the whole solar system, of course, if not the whole universe. That is the question. So what would they do if you have these three satellites and they form a triangle?
Yeah.
And you have the lasers, and they would be equidistant up to the precision of the LIGO experiment or whatever they can do there in space with the maneuver movements.
Okay.
Then you would see that a LIGO wave goes through 100,000 kilometer length distance arm, and not just a 3 kilometer length arm on like LIGO is doing on Earth. That would give you a tremendous more higher resolution. But I have not heard about anything what Rajan was told here with a single neutron being in attraction.
Yeah, I'm just saying.
That's his experiment that he's suggesting.
Yeah,
there's a G gravity measurement experiment where there is a neutron spilled up against gravity to measure the Newtonian constant of gravitation G.
Yeah,
and that is also incompatible to the value of other measurements by the torsion balance or by other means like.
And the other is a Lagrange point. I think Lagrange point may be important in this case. What do you think? The Lagrange point. Maybe you have to operate.
Yeah, that is a point. 5 Lagrange points around the sun where have no weight. That is true.
Yeah.
But how does that help on measuring the speed of acceleration? So everything is involved by information telling. Let's say we would record on a hard disk what a physical object in space records and not transmit it. Then I could collect the satellite, at least in theory, later and read later what it has collected in its bits and bytes in a perfect form on its SSDs or storage. So no one needs to have live transmission with all the problem of relativistic effect collection. When you measure where you are, and there's a good point, actually at one of these Lagrange points, and you take two opposite Lagrange points, and you measure something there.
Yeah,
with two total independent satellites.
Yeah, exactly.
And then you shoot two other rockets collecting the data and send the rockets back because you don't want to have any relativistic effects on the measurement data.
Yeah.
So in principle, that is possible.
Yeah.
But the deviation of the position of these satellites by cosmic events would have to be then recorded one way or another. So when you have a big cosmic event, like say a black hole collides with another black hole.
The
gravitational
waves.
It's a big gravitational wave, but is that movement of the gravitational wave, which comes with c, the speed of c, big enough to tell you anything about the speed of gravity?
LIGO. You need a LIGO. You have to put a LIGO instrument in the satellite to measure that.
Once again, LIGO is not measuring the speed of gravity. LIGO is measuring gravitational waves, which are for sure slower than the speed of light or exactly the speed of light. that they don't know, but I think they are exactly the speed of light. So that gravitons is a form of light.
But then, what are gravity waves? Or then, if
gravity waves are a distortion of space-time.
Yeah, but isn't gravity the distortion of space-time in the theory?
Yeah, that is what Einstein pretends, but this is not proven at all.
But that is like the okay.
No, when you have no Einstein, you have a good normal solar system. It works without Einstein. That's why I'm saying it's not proven at all.
Yeah, I agree. I'm just saying that they think. Yeah. Okay. So. Yeah, they're saying that the reason why the waves travel slower is because that gravity travels slower. So to them, the waves.
No. This is not what they say. They don't answer the question. They say gravitons are that what we measure likely because the gravitons are the information that the events have happened, and the information that the events have happened has nothing to do with the gravity. That was my thought experiment from my last discussion. When you have the sun and you're a god and could take the sun away, would the Earth tangentially fly away immediately, or would it fly away 5 seconds later? Well, 5 minutes later.
That's an old question, of course, but
it's been around for a long time. Because of the inertia. Yeah, it's because of the inertia. It will not happen immediately.
I think it will fly away immediately when gravity is instantaneous.
Yeah,
and that has nothing to do that the event of a relativistic correct graviton tells you that 5 minutes later. You will be dead on the Earth a second later due to the acceleration of the Earth if gravity is instantaneous.
One of the possibilities that it's not instantaneous, it's not infinite, but it's very, very high. The speed of gravity
it's not infinite. Yes, very, very high, but higher than c is already a violation of the theory of relativity because theory of relativity says nothing is higher. So if gravity is higher, Einstein is violated.
That's
the guy I'm trying to think of was called Andrei Kozyrev. He did experiments using. It's actually in one of Alexei's papers. Propagation speed.
The torsion and all that, right?
Yeah, exactly. Are almost instant, but not instant. In the 1950s, Kozyrev created his own non-optic experimental tools to observe true positions of stars distance from the Earth on 10 or 1,000 light years. So it's in there in his paper on evaluations of the fast speeds of propagation of gravitational phenomenon. So there's someone who did. I'm not entirely sure how the experiment worked. There isn't specific details here. I've forgotten it. But he had like a telescope where he looks at the star, but he knows that the star isn't in the same position that it looks like it's in because the speed of light is slower. But he can find out exactly where the star is based on its gravity somehow. But I really don't know the.
Interesting.
Yeah.
When did you say did he do that? In the 18th century already?
Oh no, I don't think it was that long ago. Kozyrev was. I hope not.
I never heard about that. It's interesting.
1950s. I'm going to put the paper link in the chat so you can find his name and details,
cool.
and then you can look up the actual paper then and information about it. Now I'm sure there's people out there. I know for a fact that there's people out there who say Kozyrev is a quack, and maybe they're right. I mean, you know.
Yeah, iSpace is also a quack. Unfortunately, it can do things which others can, and if he can show you that gravity is above speed of light instantaneous, then he can do something the others can't. You can always tell anyone who can do something to be a crackpot, but the life is not that easy, and the sun is rotating while the people are criticized or not with the theories or not. The theory doesn't care if you believe in the theory.
So I posted that in the chat. Yeah, Christian, just so you know where it is.
Yeah, I just opened it. Thank you.
Okay, Rajan, I don't know if you want to.
I have to say good for today.
That's great. Yeah. Thanks, Christian. That was an interesting debate.
Yeah, as usual, it's very interesting to discuss with you. I have just not given my promise. I wanted to show you the mathematical summary where you can decompose complex Rod and curl equations to pure, simple additive and multiplicative math on the lowest level, and I have not found it yet. I'm very sorry, but
okay, you can email it on to us.
I will do as once I found it. I'm pretty sure it's just on a different machine. My hard disks are not yet fully merged, I think, and that's my problem. I have to merge all my data on a single 2 terabyte hard disk, and then Spotlight will find all that again. I'm searching it and probably have never copied it to the current machine.
So that is about the curl function and the grad.
Yeah, the standard curl and Rod from the Maxwell equations, and normally that looks like magic when they're doing the typical quantum mechanical equations, but they mean not so much. Then the people interpret these kind of things like a Schrödinger equation, but when you really decompose it to the lowest level, you get very interesting insights because it's much less what you think it is actually.
Oh, interesting. Yeah. Well, Rajan, you'd be interested in that. A lot of your work is based on that principle.
Yeah, I mean, I have kind of reduced it. I don't use the tensor. Actually, the calculation from Maxwell is a very confusing thing. So, but I have simplified that. Actually, I use that, but I simplified the calculations. But
we have a look jointly in a different session once. I have given you the time to read it. It's only 2 or 3 A4 pages, but it much impressed my mathematical, let's say, non-knowledge, because I've not been a traditional physicist training or a traditional mathematical training. I'm an autodidactic person, so you can never be sure where my knowledge is from, because sometimes I don't know it myself. But I can be quite insisting that I'm right, because I've calculated things and things come out rightly.
Yeah.
And so my view is non-standard, but nevertheless hard to falsify. Whereas most of these standard equations, the people are discussing on an extremely high level, like an onion over an onion over an onion over an onion, and then interpret that multi-onion level and said, would you go please down to assembly language and tell me what you're actually doing there in detail on bit level? Yeah,
I know. It's very confusing.
And most people cannot do that. The good ones. So when you talk to the good ones, they can immediately tell you what they do. But most people are just mouth talking, quack, 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 and they tell you, this is Rod of curl of this and that, and hence this is this. I said, how do you know?
Yeah.
Actually, I believe in a derivative sequential things, that one leads to another like that. It should be possible. I think there are more than one way to do the math.
Absolutely.
Absolutely. Theoremisms.
And the more views we can combine in different equations to show the same results, like what happened with Emmanuel. When I was starting to write Emmanuel, I peer-reviewed his paper at the time. I wanted to falsify him, actually. I wanted to show him that what he's doing with his nice curved world lines of the electron cannot be the correct interpretation. Yeah. And when I calculate with iSpace, just pixels come out. And after a lot of discussions, we found out that views are fully compatible. We would have never known that.
The results there are they're impressive. Did they
on torus, right?
It wasn't the proton mass in that case.
The Horn torus of the electron, right?
Interesting came out of that. I think the fine structure constant value.
The fine structure constant via the Horn torus calculation is exactly compatible to the calculation of a total different thing by quantum Hall over Planck resistance times 2 pi. That is amazing. How can that be? And it is not an approximation similar. This is equal. It is exactly similar. So it's the same. A total different geometric model gives the exact same result. And that is really stunning.
Well, what about the issue that, I suppose I'm not even sure if Emmanuel accepts the Big Bang model, but I think they're saying at the singularity of the Big Bang, the fine structure constant equaled 1, which would mean, what would that mean for the Horn torus?
That is bullshit. There are people who calculate the fine structure constant backward in time. First of all, it doesn't go to 1. It goes from 137 in the inverse .05999 blah 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 to 128 about. So it has about 128 in this kind of reduction to the beginning of the Big Bang.
You're saying it gets smaller towards the Big Bang by a factor of 128.
Yeah, if it is not their theories are wrong. Wait. Yeah, I think their theories are wrong.
Well, what does Gerd say? Because Gerd has different values for this point.
In Gerd's equations, the constants don't change. What Gerd has is a geometrical model which takes constants of I-space and gets the right results by the model. This is how you should do it. Yeah. This is exactly what Gerd is doing is right, because either way we wouldn't have found the proton mass, and so easy. We wouldn't have had predictions which converge, not diverge, when you change measurement values by I-space values, which are just theoretical ones. And these are all indications that his differential equations are showing something real. A differential equation per se is typically physics. Yeah, you say you have a differential between the acceleration and the speed or whatever, and the position and the momentum, some relation.
Right.
And one of the relation has a higher order, like power of 2, power of 3, power of 4, than the other. And hence the differential between that higher orders needs to be solved in a way. And if you cannot solve it, then there is probably no solution to that equation. Then it's just in your brain. But if you find a solution to a differential equation, then you have physics. And all the differential equations per the sake of the mathematical apparatus needs a continuum. Hence, it should be close to I-space, but not 100% I-space. But if you have a model of continuum like Gerd's, and you have a model of I-space like mean, and they fit extremely well together, I think that cannot be coincidental. So these models build a bridge. And
circuit is considering a circuit with shunt resistance and all that. So it's a circuit. The circuit, if it's correct, then that's the proper physics.
I think his model is based on electrical engineering, and electrical engineering is fully compatible to I-space, because I-space is starting always electrical, and that's why it fits so well.
Yeah, circuitry. Yeah. I believe in the circuitry. I think the circuitry seems to be fine.
Yeah, but we have to discuss that. I really need to stop now. Thank you so much.
Okay. Thank you very much. You will see. Yeah. But we will continue a little bit. We are trying to advance it to the level of coding. We'll try our best. But you can watch the news, watch that, and we can, continue.
I think I have to clarify more of my I-space views to you, because once you have had all these sessions we had so far, but I think you still have I-space not yet in the stomach like me. You need it in the stomach to see what I can see.
Yeah, we have to apply your I-space to this one once we start coding. Then we can compare that with the I-space.
Yeah, I think the other thing you're doing, Rajan, what is it again? Something to do with the 4 vector that is to do with energy and the curl and the gradient. I find
the vortex.
Exactly, the vortex thing. So maybe we need to have Emmanuel on board to really get understanding into the vortex thing.
Yeah,
I've read his newest superluminal paper, and I'm far away from telling that I would be able to understand it.
Fair enough.
My mathematical apparatus is not on the level I need to understand that yet. So
that's it.
Yeah, I will go over that in one session. Then Emmanuel also can come because he did the experiments, so we can put all this together because he did the experimental physics. So and I can describe the math because I did it with the Emmanuel. So yeah.
Okay, but I keep you in the loop, guys. Okay, thanks, and have a nice evening.
Have a nice week, and then we'll see you next week. Yeah, thank you, Christian. Okay, so we'll continue a little bit because we want to advance to the level some coding. But next time we have to do more of that.
I mean, we don't even. I'm not sure how much you have left to get through here, Rajan.
Not much.
You're less than halfway through, but I'm just thinking that based on what you've already covered, which is pretty much the thing that we were going to code, I'm just wondering how You know, the way like with coding and computers, like everything needs to be a certain way. It has to be very logical. You know, within like within classical logical limits. You know, so I'm just concerned about how you would even go about programming this, because like not
you showed one example, spin, like spin something, spinner or something you showed.
Right. So that's
and you had done this one.
Not difficult. I mean, you can do like a matrix multiplication or between a vector and a matrix. That's no problem. Of course, but
that's all you have to do.
So you could do that, but it's just there's no point in doing it if the foundational kind of principles involved aren't nailed down. Maybe I just don't understand them. But I'm a bit confused. Like you've minus a half, but then early, So
So all values, you can take many values, right? So what I'm going to go, So essentially, this is just to show that I can connect the matrix to the actual XY, the graphing. Okay, we'll go that later. But that's not the main point. The main point is when I come here, see, this is the main thing. What we are trying to achieve by that calculation, right? I can plot QL versus QG. I put different values for the matrix. I get QL and QG values, right? I'm just showing here schematically, so you can get a map. You can actually plot it, get a scatter plot, right? So that you can do with the calculator, and the same thing with computer. Computer does it more faster.
Right, and so these are values you've calculated yourself.
Or these are the values
And
so that's the values I calculated, but you can do more with the computer.
A line fit there as well, theoretical prediction.
So what happens? My prediction is that when you actually do the calculation, right, you will see a band here. I call it the anomaly band. You will see, because the QL and QG restricted by the physics, because they are quantized, you cannot have all the values. So there will be a band in between, which I call the anomaly band, and that shows, so the regions are like superluminous, right? In that band, something is happening. Okay. So what is happening? I'm describing here what is happening. I don't know why it got image. Okay. What is happening is that you can think of a clock. We can discuss more next time, but you can think of a clock, right? And when it's in the superluminous thing, the clock is a quantum relativistic clock, so you can only move at the speed of light, right? The superluminous level, it gets frozen. That's frozen because it reaches maximum. It cannot go beyond the speed of light, so it gets frozen there, right? Same thing happens with the inertial, very high, like a black hole, very high inertia.
Wait a second. Wouldn't it start running backwards as it goes faster than the speed of light?
No, the clock only runs only one direction, right? Clock can go only one direction. So it keeps moving faster.
Like the quantum clock, things can move either direction.
Oh, yeah.
Time reversal.
Yeah. So let's say start with a relativistic clock, right?
Well, so but then you still have the same problem with the relativistic clock as well, because you have the Big Bang and entropy moves forward. But then if you had a big crunch model, entropy would be moving in reverse, so time would be moving in reverse. Also, if you go faster than the speed of light, your time is going to go like the function goes up, and then it starts going down the opposite side. And once it does that, it goes into like, square root of minus I. So, or square root of minus 1 being. So you're into imaginary time, which is some other time issue. So time is just moving in a different dimension.
But essentially
it'll probably be backwards in time, I think.
No, you will see the clock is frozen essentially.
No,
the real clock, will be
at exactly the speed of light. It's frozen. Beyond the speed of light, which is impossible in the model anyway, but assuming it's possible, time would have to either go into imaginary time, or that could be the same thing as going in reverse.
So you say only in the vacuum it will be frozen?
No, well, yeah, I mean, if you're saying that the speed of light is only the speed of light in a vacuum, but I don't know if that's true, because they talk about the speed of light as not being that important. It's the fact that it's the speed of causality. So it doesn't matter if it's in a vacuum or not, because causality happens everywhere. Do you know what I mean? So like if you were on a spaceship going at the speed of light, you wouldn't be in a vacuum, because if you were, you'd be dead. But time will still stop on the spacecraft, at least from the point of view of everyone else. So the clock will stop on the spacecraft at sea. But if you go beyond it, then it's going to move into imaginary.
So you say it will go like this?
Some sort of, yeah. I think it goes when I saw the plot, it goes up and then it starts going down the other way. So, but I don't know what. Maybe there's some dividing line. I mean, the imaginary axis is in the y. In a sense, the real axis is on the x. But if it's but if it's a complex plane, maybe that's something to do with it. I'm not sure. I've forgotten. I've seen the graph though.
But in the inertial thing, it will be frozen, right? Like in black hole, if it is very, very high inertia goes to very high level, close to infinity, then the clock will get frozen, right? It will not move any further. It will be slower and slower and slower. Then it gets stopped. It will be frozen there.
Well, yeah, it'll like around a black hole. The issue there is you have a very strong gravitational field, and clocks slow down inside a gravitational field.
And then eventually stop, right? It'll be frozen.
Right, but I would say it stops at the event horizon. And what happens to the clock once it goes beyond the event horizon? That's an interesting question. I would say that it's the same issue. It's now going, in effect, beyond the speed of light, even though it's not really traveling. But it is. I mean, that's like saying something falling to the ground isn't really traveling. So it is moving, and it's probably at the point that it crosses the event horizon, it's now going faster than the speed of light, and it's essentially left our universe so it's now an imaginary time. So we don't know what's going on there.
I cannot plot like this. You're saying I cannot plot like this.
Well, actually, that plot is quite good, because if you were saying that time is 0 at the top, let's say, and full at the bottom, then as it goes up to the top, it reaches 0, and then as it goes beyond the speed of light, it starts to move again. So your plot is accurate.
Okay. So see, I am not plotting actual velocity, but the state of the clock and the environment. I think that's
what I'm saying. Right? No, I'm saying that
should be fine. Yeah.
The speed is at the bottom, though. You're going from presumably 0 speed to superluminal, and then the y-axis is time. I'm saying would be correct, but you'd want to invert the graph essentially. But let's say 0 is at the top, then as it's getting faster, it reaches the center of the graph where c is, then time is 0, and then as it continues on, time goes into an imaginary.
So I have to put upside down like this.
Yes.
If I want to show the normal thing, but I think this will still be okay, because what I am saying is that whatever is the maximum or minimum, so it should be minimum at the vacuum, right? So it has to go like that, and minimum at the vacuum goes like that. Okay. So then even then the anomaly will start moving. What I am saying is that the anomaly band will start oscillating here. Okay. So this is what we may see in the anomaly. See what I mean by anomalies in this superluminous thing. So I'm connecting with this stuff, what I showed in the top, this one. So what happens here? It says the clock according to the superluminary, it starts going backward. The anomaly thing, you know, it reaches, you know, the clock is real. It starts moving. Okay, here it's negative, but when it goes negative, I think negatively also it can stop, right? It can go all the way negative and then stop also. But isn't that possible?
Well, no, it'll go. The time will be running normally, and then as the speed increases, it will go to 0 when it reaches the speed of light, and then it will start going into the negative, let's say, after it goes beyond the speed of light into, you know, superluminal. So
okay.
I think
so the clock
negative is what I would say is the proper interpretation of that. But
okay.
I think the mathematics just say that it's an imaginary time.
Okay. So suppose, so in this region where the anomaly is, you can actually see the clock moving. So it is in the, you know, it is less than the speed of light. So it can go faster and faster depending on the inertia and things like that. And that's what I see. It starts clicking until anomaly gives rise to, for example, hot PDP circuit could be a clocking mechanism here. That's a mechanism. And then until a particle is formed. When the particle is formed, then it becomes, you know, normal inertia. So the clock will start normally. You know, it will start moving according to the particles. Different type of particles will have different clocks.
Is the point of this to describe particle creation?
Yeah, particle. Yeah, particle in terms of the clocks instead of space. You know, so in terms of time.
Yeah, so you could just have like a sort of you know, an ether or like 0-point energy field or whatever you like, and then it's just noise, yeah, in a sense, and then in the noise vortices form, and at the center of the vortices, it's like you know, the pressure gets intense, and then the particle comes into being.
Yeah.
Is that not? Yeah. So
yeah. So eventually a particle will start forming here.
Yeah, like
so that's the idea.
Vortex, and then it's like
yeah.
I don't know.
It started. Yeah. So
that's fine.
Once the particle forms,
I think, but it shouldn't. Yeah. So, but I'm not sure I get everything else around the whole. What would be the sort of the first step in describing that? Or it seems to me it's a bit like what you were talking about earlier, where you know, when you spin water and then you get this empty space in the water, it's a bit like the particle is almost no longer in our space in a sense. It's like a hole in space, but because a hole in space doesn't, if a hole in space looks like a bright particle or energy, it would mean that the negative of the universe is actually a positive energy, which would mean that space is like a negative substance or something. You know, like a bit like Dirac-C equation. Which is actually follows from Dirac-C, doesn't it? I think.
Oh, you say that when the particle leaves that, when the phase, like we are showing here, when the particle, let me see, the particle evaporates. Let's say this is a condensate, superluminous condensate. So when the particle evaporates into the subluminar space, then it leaves a hole here. Is that saying like a Dirac hole?
Oh, well, no. I was just talking about your earlier theory about, or concept about the black hole that you and Manuel were talking about. When if you were to like
hole,
when or even just a full, like a rotating black hole, when you rotate water, you get this hole in the water where the vortex is, where it goes down, and then that is like no water is there. So it's a similar thing with a rotating black hole.
Yeah.
Enter the black hole, there's no space. In fact, it's a strange concept.
Empty. You mean like a vacuum, almost like a vacuum.
Yeah, almost. Who knows what's going on, really? I mean, but maybe it's a different space. You know, it's like it's a hole in our universe. Anyway, that much is clear. So, but I'm saying that if you have the same concept in the ether or whatever this thing is, so there's a vortex happening there. At the center of that vortex, the hole that is formed is the particle. That particle does have energy. So if the hole in the universe is some sort of highly intense energy formation, that would indicate that, you know, a minus times minus equals a plus. So the background ether must have been in a negative state before the particle emerged into existence.
It's interesting. Also, it can form a wormhole eventually, right? It can form a wormhole. That hole can become a wormhole.
Yes, that's the theory. Yeah, it's a great theory.
Yeah,
really cool.
So I think the wormhole, idea of a wormhole may fit in there, because if that hole, it start connecting with another one somewhere else. Let's say a black hole. Let's say it's a chiral black hole. The left-handed black hole connects with the right-handed black hole, and they form like a wormhole. You know, the hole starts connecting, and they form like a wormhole.
Oh, interesting. Well, yeah. I mean, I think there wasn't there an idea of a black hole and then its opposite, which is like a white hole. Which I mean,
white hole. Yeah. So white hole may be. Yeah. Actually, white hole may be. I don't know, chiral. If you talk about chiral thing.
Oh, interesting. Yeah.
Yeah, I think the chirality, left-handed, right-handed, may be involved, because.
But I mean, couldn't you have like a star that's spinning the opposite direction to another star?
Yeah, I think it's possible.
And then, okay, so then let's say both of those are very heavy stars. They both collapse, and they're going to. They are going to retain their angular momentum property. So they're going to be spinning in opposite directions.
Binary, it's a binary.
Well, yeah, but they don't have to be in orbit around one another. They could be at opposite ends of the universe. So
they can be.
At the end of the day, the process that made both of them is still the same. They both collapsed. So how does a white hole form? I mean, how is a white hole any different to just a normal star? You know? Maybe there is a big difference. You know?
Maybe, I think the idea is that, for me, I think the left-handed black hole and right-handed black hole, and they connect from wormhole, may be more plausible than a white hole and a black hole, because white hole essentially is, like you said, maybe same as a star. I mean. So,
right. But from the point of view then, like anything falling into the black hole, you could go into the black hole and then come out of the white hole in a different place. So that's a wormhole. But you couldn't go the other way, you know, because there's unless you're going really fast. And also coming out of a star is just, that's not going to work either. So, but then in your thing, I like it. I like the concept because it reminds me of the magnetic monopoles. Although they are both spinning in the same direction, they're connected by this tunnel. So if you were to go into, so it wouldn't actually be a chiral thing, I don't think, unless it's a higher dimensional thing. But if two black holes are spinning in the same direction, maybe at the exact same speed, then you could go in one and out the other, assuming there is some relationship here between black holes and monopoles and magnetic monopoles. Or maybe if you could have a big enough magnetic monopole, I don't know if that's feasible. You could use that as a wormhole, but then maybe not. Although if it was in this superluminous kind of concept, maybe. So yeah, I mean, I'm just floating ideas there, Rajan.
Yeah,
really don't know.
But in order for it to come out, in order to go in one of them and come out the other one, they have to be spinning the opposite direction, right?
Well, no. If you fall into a black hole, whether it's connected to another black hole or not, how are you going to get out of either of them? Because It's just, there's no way, unless you're talking about some sort of, the laws of physics break down and then you're spat out. But you could be spat out just outside the black hole and then fall in again, or you could be spat out like millions of years in the past, or I don't know how it works. I mean, if the laws of physics are supposed to break down inside them, then literally anything could happen. You could come out and you could be the Eiffel Tower or an elephant, or you could be,
it becomes spaghettized.
Yeah, that's right, spaghetti sized. But that's when you fall in. So you're going to be completely destroyed. So all of the atoms that do like emerge, but then you're also going to be stuck just on the event horizon. I think they say you're going to be frozen in time there. You're also going to fall in. And I think there's that issue that you could just emerge back out because of like quantum fluctuations. Hawking radiation possibly is
exactly.
But certainly quantum fluctuations, and you would just find yourself outside the black hole. You could be completely intact. So it might not, but would you find yourself outside a different black hole that it's connected to?
Oh yeah,
that's
binary black hole type of thing.
But would it be worth it? Is the question. Because you could be in there for like millions of years, because time stops inside.
But the wormhole, suppose it's a proper wormhole, like a tunnel, then you won't be there millions of years. You can come out much faster.
Yeah, and actually, I know Kip Thorne wrote a book on wormholes. Are the mouths of wormholes always black holes?
No, they are part of the black hole, but they are not black holes.
Right. So the wormhole is essentially a different object.
It's a tunnel. It's like a tube or tunnel that connects.
Yeah. But what creates it?
What creates originally is from white hole, but it's actually, you say there is a hole, right, in the middle of the vortex, right? That hole, suppose it can connect with the other hole from the another black hole. If these two can link each other somehow, right? This hole and that hole can link each other in space. So there has to be something.
I'm not sure if I agree with Kip Thorne on that then, because if you're flying into a black hole, you're dead for a start. And also, if you were to get past the event horizon, pressure and all of that, plus the time issue, time would completely slow down. But it wouldn't slow down for you. It would slow down from the perspective of people outside. However long it takes you to journey through the black hole and out the other side would be possibly millions of years for the people you leave behind. But then you would get to the other side of the universe rather quickly, I guess. But everyone would be dead, right?
Yeah, but it depends. It depends on the type of wormholes. There could be more than one type of wormhole. Suppose it connects nicely.
Do they all come from the same creation? They all come out of this black hole creation? And if so, then how do they differ from one another?
How they interconnect? How the hole from one of the black holes? How they connect with the hole from the other black hole? Because if they are not nicely connected, right? Then you have a lot of problem in between, like maybe dead before you can. Suppose it is nicely, smoothly connected, right?
Yeah.
So it as soon as falls into the black hole, it goes in the wormhole. Then everything starts going smoothly until you go to the next one.
Because there's no singularity there to crush you.
Yeah, the idea of singularity is the main thing. If there's no singularity, you won't be dead.
All right, you're just moving at really high speeds, but you're not going to be squashed to bits. Is the concept?
Squashed, yeah. Something protects you. Some envelope or something is protecting you.
There's no direct singularity there. It's just a tunnel through like four-dimensional space.
Yeah, exactly.
Yeah, okay.
So no singularity there. Yeah.
Okay, but if there's no singularity, if there's no singularity, then what's causing the high gravitational event?
Yeah, it's a vortex action. the vortex is moving at very fast speed.
Oh yeah.
It's speed
Okay.
of light or very fast speed that is sucking in like a vacuum. It's sucking in.
It's a gravitational. I mean, wasn't it a star, that a really heavy star that's collapsing?
Collapsing, yeah.
Yeah. Okay.
More than
then
the Schwarzschild. The
Okay,
Schwarzschild radius.
Yeah. Well, we'll just accept Kip Thorne's and other people's proposal that this thing is real, and that's all I can do at the moment. It sounds like he did the equations anyway, and it was valid. So I'm not going to argue.
So what we can do is, if we can plot this, I calculated very simple, but all you need is more calculate like this one. We can get a plot like that, and then somehow apply a Q factor from GERD and show that there is a band that's formed. It's very similar to your anomaly in your earthquake and things like that. Very similar. It forms like a anomaly band here. Then I think we can show that anomaly band is a rightful place where a particle can form because of PDP mechanism, things about PDP mechanism. That's one of the things we can show. So all we need is a plot of all possible QL and QG values, and we plot them and then show that there is a band, there is an anomaly band. Like
when you say all possible, when you say all possible, you're talking about 1/2 and 1/4.
Yeah,
it could be literally any value.
Any value, but it is limited. It's limited by the Q factor, which means that you cannot have all the values. Like I cannot say there may be discrete values. They are not continuous values.
Oh,
you can have
okay.
one half,
what makes them
1/4, 1/8, like that.
Right. Oh, okay. And the Q factor means it's going to dampen. So
it will not make it discontinuous. It makes it discontinuous.
It won't get to it will dampen to 0.
Yeah, right? It won't be exactly 0. Only these are zeros. These will have 1/8, like a factorization, prime factorization. You can use even prime numbers. Maybe it will only factor up to primes. So we can use prime. You can use prime instead of this. So I can say 1/, instead of using 1/4, I can use 1/3, 1/7, like that. Let's say it's priming, it's factorizing into prime factors.
Okay.
That's something. Prime factorization is something we can use. So, just for simulating. So instead of 1/2, 1/3, then 1/5, 1/7, then 1/11, like that.
Right, but if you're using the Q factor, it's going to decay.
Yeah.
It's going to decay a lot quicker than that, I think.
Yeah. But initially we can do that and then see how the Q factor will affect that. For simplicity, to start with, we can use the prime thing.
Well, I think for simplicity's sake, we should just use the values for 1, the value for 0, and then the value for 1/2, which is like a quantum thing.
Yeah.
So it's halfway between 1 and 0. Yeah. And that will give you how many values? You'd have 1, 2, 3, 4, 5, 6. So you'd have 6 potential values, and then you're choosing 4. So it's 6 choose 4 equation, which works out to 15 matrices, doesn't it? 6 choose
something like that.
4.
Yeah.
Right. So okay. So you have that. So you have 15 matrices, but then they are multiplied by your on/off.
Yeah, which is 1 and 0. 1, 0.
Yeah, or 0 and 1. So that will give you a total of 30 unique answers.
We can start. We can use Q factor to find that stuff.
I'm just guessing that it will be 30 unique answers. Does that sound right to you?
Okay. Yeah, probably.
because
yeah.
probably 30. Because it's two things times these 15 things, so that's going to be. But then some of them could turn out to be the same. So we might end up with, because I've noticed that with the spinners, that when I did them out, some of them actually equaled 0 and 0, and some of them equaled each other.
Duplication.
So, yeah, so they weren't all unique.
And use prime. If you use prime, you can get unique prime, like 1, 3, 5, 7.
Do we
1 over 5.
Do we even want unique values? I mean, it's interesting to see if they would kind of collapse down, because I mean, you know, it's a spinner thing. You've also taken the
1 over 2.
Thing, so no. So then you'd have your
1 over 2.
So it'd be interesting to see how many you'd actually have at the end. And then what do they correspond to at the end of the day? Their time is on, time isn't on. Local time is on. Global time is off. What does that mean? Physically, or does it mean anything?
Okay. So I believe that it's like a network, like a fabric. I have put it here, like a fabric. You have like a fabric, right? So you have like a twining network. Like you have global time, you have a local time there. They are like forming like, you know, like interweaving, you know, interwoven fabric. So they form eventually fabric of space-time kind of. So suppose you are on this fabric, right? On this world line, it can move at the speed of superluminal speed. But once you hit on the fabric of the timeline, then it's subluminal. So at the nodes, you have the vacuum. The node where they intersect. The node where they intersect.
Reminds me of what you're talking about is what is it? The geometric. You know, the way you have all of these different universe models, and one of them is called geometrogenesis. Have you heard of that? Geometrogenesis, meaning the birth of geometry.
Really. What is that?
Space was created along with the
geometry.
universe, and so essentially there's like a network like you're talking about, which has infinite numbers of dimensions. So there's so many connections in this network because there's so many dimensions that it becomes meaningless. But then as the universe grows, like from the Big Bang, the connections start breaking, and then you're left with just space-time is the final network that you're left with. So I think somebody who works a lot in this area is that guy that Christian's always talking about, Stephen Wolfram. You know Stephen Wolfram, obviously, and he's big into hypergraphs. So he's constantly trying to the category theory thing where you're connecting one category with another. So I find that stuff to be a bit difficult to comprehend, but what I have kind of recently discovered is that you could take category theory, which is really just a data frame with a load of features on the top. So whatever those are, space, time, energy, you know, etc. And then you have the index down running along one side, and so you have all of these values. But it is possible to use those data frames as like a Cartesian coordinate system. So then you could link it with an algebraic equation, for example. So you could have all of the values for x that the x can take, the function, running along the top as the features, and then all the values that the y function spits out, essentially, and then the index. And then you simply plot them into the data frame at a certain point. Then you could graph that. So then there's a connection between category theory and algebra. And then if you can go from category theory to algebra, you could go to differential equations and then to space-time, if you like, you know, something like that. So I think that's plausible, and you could also probably do multi-dimensional. You know, you could have infinitely large dimensional data frames. Technically, maybe you would use, or you could have. Well, maybe you couldn't store it on a computer, but maybe you could use them in a group theory sense or something like that. But yeah, so you could have pretty large ones though. You might not be able to get back to the start of the Big Bang, but you might be able to get back, you know, within a few seconds of the Big Bang or something, because I'd say that the decay is probably exponential. So yeah, I don't know if that's any help to you, is it?
Yeah, I think that eventually we can do that. We go one step at a time. Like we calculate these, like you said, you can use a prime thing, so we can get large number of points there, and we can get the plot of QL and QG.
So you'd be concerned that, you know, 30 points or less, that wouldn't be enough.
Yeah, you need a lot of points actually.
That
so if you use a prime, say it's factorized somehow, like we said before, magic square, but in this case a prime factorization. So it keeps factorizing until it reaches a prime level, right? So you cannot factorize anymore. So I think lot of repetition is because
there's an infinite number of prime numbers is what I was going to say. So what's your range?
No, but we stop at certain prime number. We go up to, you know, we want to collect like 100 or 1,000 points at the most, you know. So we can go up to certain level. Like
what's the justification for using prime numbers in this situation? I mean,
because everything gets factorized. The idea is that it is something like you have a repetition, right? QL and QG are repetition, but this repetition get factorized. You know, the repetition is like redundant things. You know.
Are you saying representation? Or
yeah, it's the same thing. It's the same thing. It's representing the same thing, but it gets factorized. When it gets factorized, then they become unique. You see that? So once it reaches a unique point, then it won't factorize any further. Then that stays. That value stays.
Oh, right. If you're saying that you have QG, QL, and let's say they're both the number 36, and then you factorize them in prime numbers, then you will wind up with like maybe 3 unique values, like 1, 5, and 7 or something.
Yeah,
well,
something like that.
Well, that would be 35, let's say. So I guess, I don't know. Yeah, that sounds about right. So you could give QG could be 5, QL could be 7.
Yeah.
Then what about 1 over 7? Right. So you're going to take the inverse of the.
Yeah,
that's okay.
Exactly.
But then what if there's more than 2 prime factors? You just take which ones? How do you know which ones to take?
Then it repeats, right? Repeats. So the QL can take 1 over 7. The QG can take 1 over 5. They can change the values each other, right?
So you're looking at permutations over all possible number of factorizations.
Yeah.
And
so with that, you can get a lot of points. If they don't repeat, then unique points you can get like 100 to 1,000. You know, and we can stop the computer that time. You know, so it may be like you have to go up to maybe 100,000 at the most. Prime factor up to 100,000. I don't think you need to go further than that. Maybe 10,000 or 200,000. I don't think you need more than that. The prime numbers. I think your computer can find that easily, right?
Yeah. That's not a problem.
Then you just invert it and then switch it around, permutate it, and that's it. So when you get enough points, I think when you plot it, you know, there's a rationality. We already said that any factor, like even Christian does that. He factorizes, not necessarily prime factor, but he does factoring. I think the factorization is a primary thing.
Yeah, he factorizes like big physical numbers or whatever, and then he usually gets out. Obviously, he gets out all these prime numbers. Those prime numbers sort of feed back into his work in terms of like whatever constants he's using. So
yeah.
so it is
So
interesting.
then he ties a physical meaning for that, geometric meaning for that.
Right, and then
And
I
I
said,
think
in
your
your,
crystal,
in your situation, you're taking time, you're taking all of this black box stuff, transformations,
yeah,
and using that to turn space time into just time.
yeah.
You should show me
So
how you're doing that. Actually, that sounds pretty interesting.
yeah,
Maybe another
yeah,
time.
yeah, another time. But we can do this. If we can do this, I think we can get out, and then you can connect with your 600 cell, 24 cell, or whatever. Uh,
Yeah. Well, work is going on there, so it's I'm still working on that. It's going pretty well, but I don't have anything.
okay.
Well,
So
I
we
do
may
have,
connect with that.
still
Yeah, the
it's
prime
still a
factorization.
work in progress. So, but I do.
Yeah,
I'll tell you what I have been working on.
Okay.
On that, where is the program?
Yeah.
Oh, this program. It's called. And then I don't need to share the screen. I just need to just remind myself what I have.
Okay.
So essentially, I have the coordinates of the 24 cell, and then I have, how do you say it? I've created an isomorphism between that and the permutations of S4.
Uh-huh.
And then from there, created
Uh-huh.
an isomorphism between that and the permutations of S5. Then I'm using the conjugacy groups of S5 to form, hang on a sec. Oh yeah, I'm linking it with the polytope number of the 600 cell, and then gradually through that process, that's the exact same process that I used, by the way, to link the 24 cell with S4. So I'm just doing it now on a larger scale, the 600 cell. And so I've got 24 coordinates of the 600 cell locked in. And what I need to do from this point is rotate it's quite complicated actually, but I need to rotate the 24 cell to its dual and then see if those coordinates map to the dual matrices of the 24 cell. And then, then I should be able to put the particles in. But I've probably made notes on it because it's pretty I don't know if it's possible yet, but I've tried a number of things and they've all failed. And then I had this brilliant idea of using the Klein quartic. Then I realized that's not going to work either. So this one is the one. Hopefully this works. Okay. But it should be fine because actually the conjugacy groups map to S5 and they all have they all start with either a 1, a 2, 4, or a 5. So we can just fit the 24 cells into those 5 groups because there's 5 24 cells in the 600 cell. So once we start rotating, it should be okay. And you could also try that for coding next time.
Yeah.
That might be interesting.
Can we code what we said now about using the matrix and then just a prime thing, 1/7, 1/5, that kind of thing, and get like 100 to 1,000 points? Can we do that coding?
Yeah.
Okay. So we'll try next time. By next time we'll do that. What I want to throw is that I think I can connect the QL and QG to the Bohr the hydrogen atom, the quantum aspects. You see that the hydrogen atom has 4 things like principal quantum number, azimuthal quantum number, magnetic quantum number, spin quantum number, right? I can connect, I think, the QL and QG to that. So then we can describe the quantum mechanics of the hydrogen atom from this one and see how they, how the coupling aspects, how the particles come and how they form hydrogen, and that forms star and black holes and all that things. So that's the eventual goal. But I think we start with this coding, what we mentioned now, simple way.
That looks interesting.
Yeah, and then we can move on to this. This is from the
Well,
literature.
yeah, I suppose we should see what the results are and if there are any.
Yeah, exactly. And then how does it compare the Q factor?
I think
Things
the
like that.
idea was that you were linking it to quantum entanglement.
Yeah, eventually, yeah.
But I thought that the point was you have these fluctuations or permutations, and if one permutation is the same as the other, then that indicates that those two things are aligned. So what actually you want to get out of it, Rajan, if this is your goal, let's say you take those 15 matrices I was talking about, and then you multiply them by the two vectors, then the ones that turn out to be the same would indicate particles that are could be entangled with each other. Then at the end of the day, so like, what does that mean? That's the problem.
Yeah.
Like,
see from here,
like, let's say you have a particle and you have all possible permutations, and then so you're saying that I guess one particle goes through a state change, arrives at one value, and another one somewhere else goes through some sort of state change. I don't know what's bringing these state changes on. I don't know. But whatever it is, then if two of them have the same state change, then they become entangled. But that wouldn't make a lot of sense because they could be on the opposite side of the universe, have no interaction with each other, and become entangled, which wouldn't make sense. Because usually, like, you create an entangled particle, like you send it through a beam splitter, something like that. So your equation would have to deal with something to do with going through a beam splitter, particle going in two different directions at once, or and then those two are entangled. Yeah, something like that. And then you could have the spin, obviously, because the spin is a big part of entanglement.
Mm-hmm.
Not sure what the time and the local time, but I could see how, if they're infinitely distant from each other, and then you change the spin of one, it's going to change the spin of the other. So then you'd have maybe your 4-vector time would come into that because you have local and then global time. So, what would that mean?
See, the idea is to find a wave function. See, from here you can find the Q factor, which is phase angle. You get phase angle the wave function, then we can figure out about entanglement from there. So we have to back calculate inverse transform, or back calculate the wave function, and and then we know that we are going to use the phase angle. So how they match together,
Oh, right. It's quite a big thing on the back end there. I mean, maybe. I mean, this is like once it gets into phase angles and
wave function. See, once we know the wave function, we know whether it will entangle or not.
Oh, okay.
The spin wave, the wave function, the spin wave function. Then,
well, I mean, you're kind of already there with these matrices anyway, but obviously they're a model thing, I think, and
they're all interlinked. See, they're all derived, but how easily we can inverse transform, that's the thing. We'll worry about it later, but I think it's possible. We may have to do what I call as the trial and error method. We may not be able to get it directly, but trial and error method. So we have to put some wave function and then see what is the value of QL and QG is. So like that we match, and then we get two graphs, we match each other, match the two graphs.
I think I would like. I'm not clear on the how do you say the word? What's that word? The justification behind all of the steps feels like your process here is, what did you say? Like trial and error, which is cool.
Well, the thing is,
this is a very, you should be using what you're talking about, where one step leads to the next.
That's actually it is that. It is that.
I don't. But it's just you're starting from a step that I don't understand, so I can't verify if this is correct or not. It's a bit like with the PEP circuit, where I couldn't understand it. Now I do, and I get, and it's very interesting. But I think with that, what you're going to need to do is you're going to need some experimental results before you move to the next phase. So you're going to have to prove that what you're saying is correct experimentally. Otherwise, can you do that though? Because what you're dealing with is at like what is it, 10 to the minus, beyond the Planck scale. So I don't think you're going to be able to prove it experimentally, are you?
No,
or have you thought of it?
No, but once we plot this QL and QG, if we find this anomaly band, that then we can use it to connect with the experimental thing.
Yeah,
and we have the wave function and another one.
I don't see the connection though. Am I missing something here? Yeah. It's interesting, but I just don't see the. You've got world line and timeline, so actually, yeah. I mean, it is interesting, but like I have a different view on world lines and timelines, I think, to you, but that's only because I don't fully understand. Well, no, I do. I get what you're saying, but I don't fully understand what you're talking about. It's cool.
Yeah.
Well, I don't know what you're talking about.
No, what I'm saying is that.
Although I do like your other, I do like the other idea a lot with the matrix, the four with them, and everything is when all of them are at play, it's energy, and when one of them at play, it's like curl or gradient. I think that one is much more clear to me. This one was clear to me at the start, but as it's going along, I'm getting more and more confused.
No, I think we have to calculate. We have to do a simple calculation. I think that if you do the coding and then simple calculation like this one, we get a plot, and then we interpret the plot. It'll be much easier to understand.
Yeah, well, I mean, I suppose you know what the plot's about. So next time we'll try and plot it. That's fair enough. I might even try and plot it over the weekend or something.
Okay.
Okay, Rajan.
Use the prime numbers.
You know? Yeah, I already have the prime factor thing, so I'll just no problem.
Just plot it, and then we'll go from there. Because I think without the plot, then one step at a time we'll go the graph. Now we go one step at a time, each plot. And then
I'll do this plot, and then I'll send it on to you, and you can sort of interpret it, see if it fits into you.
Yeah, that sounds great. Yeah.
Okay, no problem. Okay, see you next week, Rajan. Bye-bye.
Okay, have a nice weekend. Thank you very much. Yeah, have a nice, wonderful.
Okay, wait a second. I'm going to click off end that.